You're just like whispering.
The space economy. In the space economy, so in this framework, we've published the Space Venture Europe, which is an annual survey. The idea here is to monitor the level of private investment in the space sector in Europe. A lot is being done regarding what takes place in the United States, but we have really a very specific focus on what's going on in Europe, and especially regarding the startups. We have a bit earlier, we had already published a report on the rise of private actors in the space sector. And we have touched a bit on space exploration through a report trying to assess the potential contribution of private actors to space exploration. And I guess it was an interesting one that you might want to have a look at. Our second pillar or third pillar is space security. So in this framework, we have published a report on space and security in outer space, and the idea was to assess the potential of a transatlantic collaboration in this domain. And as an outcome of this report, we have issued a report on space defense, so which is Europe Space and it's called Eurospace and Defense, but the idea is to I would say assess and to maybe make some recommendations in order to be able to move from space defense to the defense of space, which becomes a topic in itself. And in the same spirit, we have also issued a report on the space traffic management and proposed European perspective for the space traffic management policy. And this one has raised a lot of interest, and we are now involved in a number of consortia that are working on this topic in the framework of studies that have been launched by the European Commission. So, but there is, of course, much more. You will be able to find on our website a number of other public reports, one on European Space Weather Services, one on European-India Space Cooperation, more focusing on potential perspectives at industrial level, one on the measuring space power, which is basically making the nuance between what is a spacefaring nation and what qualifies a nation to call itself a space power. So the idea is to assess where Europe stands in this respect. Interesting question, actually. Another one on the evolution of the role of space agencies, especially in light of the new space models development, and which of course raise a number of questions regarding the mission of the space agencies as development agencies, and one of course on the COVID-19, where we try to assess the potential consequences of the COVID-19 on the European space sector and on the European space industry. So we also publish a number of of reports and books in collaboration with the Springer. So some that we write, some we are just editing, so calling for contribution. We receive articles, and then we rank them, we assess them, we put them together, and then we publish them in a book. So for young researchers, I think it's a good way to be published. So I just mentioned a few here. You will find much more on our website, but I cannot go through the whole publications that we have issued, even over the last 2 years. It would be too much. So I don't want to take too much of your time, but I guess that it was, for me, at least a good opportunity to let you know more about ESPI. But if I was successful in raising your curiosity, then you can visit our website. We can follow us on Facebook, Twitter, YouTube, LinkedIn, etc. Thank you very much for your attention.
Thank you. It was very interesting, and we can also forward the contact details and the Facebook links in a email chain. We can gather them all, and at the end of the day, just send out an email so everybody will have the contacts. So next about EuroMoonMars and the exciting projects that we're doing. Are you using your own? Yeah. Okay. This one, I think.
Yes.
Okay. Oh no, this is the old one. Okay.
Yeah, okay.
And if you want.
So let's see. So that's the presentation I gave yesterday. So to ensure that I don't show you the same slide, I've put the two in one. And yes, yes, yesterday we had a session at the Vienna Observatory about astronomy from the moon. And here I would like to talk about what EuroMars, our platform that we developed with the International Lunar Exploration Working Group and the support of a number of agencies, ESA, NASA, and others, and industry and academia, what we have done. I think that I'm allowed to remove my mask when I'm a speaker. It's a privilege when you speak. So I would like to discuss in particular in the context of this habitat workshop, what we have been conducting in terms of space habitat studies, and in particular in areas of field simulations. And so this is a platform we developed more than 10 years ago, starting at ESA, but with, led by the International Lunar Exploration Working Group, with the collaboration of NASA and others and universities. And every year we have a group of young professionals that are joining us. So I have put those in the last 4 or 5 years. And they are doing internship or they are collaborating with us. And after when they move on in their careers, hopefully they continue also to spread some of our research and other activities. And so this goes in line with the roadmap for exploration that we proposed more than 20 years ago with this International Lunar Exploration Working Group, starting with a phase of precursor mission in orbit, then a phase with a surface robotic village. That's when the idea of a moon village was proposed more than 20 years ago, and then leading to a human base with robot, and at some stage with permanent presence and sustainable operations. So working on these guidelines, we have used some of the data from previous lunar missions, and the one I was involved directly as a father, and the project scientist was a smart one. That was the first lunar mission of this millennium. And eventually, for the purpose of future moon base help us to map very interesting areas, in particular in the south pole of the moon, where we identify the places where there is permanent shadow and possibly reserved for ice, but also you have near Shackleton crater, some areas which are always illuminated even during the winter. So this is a kind of cartography of a south polar region that we put together from SMART-1 data that would help us to place various assets, some at the pole, some on the far side, some inside some craters, and so on, for an overall infrastructure that could support future human bases on the moon. We even found a place close to the South Pole itself, which is a peak of light, and that we could monitor during the whole year. We could also establish its altitude, and from there we have shown that we receive almost all the time sunlight. So that's a very interesting challenge actually for Space Policy Institute. Help us to say what will be the status of this real estate. So we have the Outer Space Treaty that says we cannot be owning any piece of land, but there will be a rush to put some scientific artifacts there to claim the use of this place, and how can we share the benefit of having, for instance, a solar powered tower there that could be distributed to partners, or are we going to commercialize its use? So it's I think, quite interesting also set of questions that have a relevance for space policy and legal and commercial aspect. So now, where are we in terms of human activities? So from the ESA side, we have 3 key destinations: low Earth orbit, where at the moment we have the International Space Station, and this is now continuing with funding until 2024, and it's being discussed how this would be extended for operation, eventually also by putting in more commercial exploitation to lower the cost of running the space station. But now the next destination for us is the moon for human spaceflight, and we have a set of programs that had been approved in the last decade, including building 2 ESA service modules for bringing an Orion capsule around the moon. And now this has been integrated in the overall NASA-led program called Artemis that will see the first automatic mission with this capsule for 4 astronauts, but empty, launch in 2021. But then from 2023, we'll have 4 crew on board, possibly the first European also around the moon, maybe the first woman as well. And for sure, also in 2024, there will be 2 astronauts going from this this mission to the surface of the moon, and this will include the first woman on the moon, which to be American for the first one. And then you will have a succession of a mission of Artemis collaboration every year that could lead within 2030 timeframe to have a sustainable outpost on the surface of the moon. So at ESA, we also developed further the concept of a moon village, which has in some part the vision to have this sustainable human presence on the moon, but also is trying to engage, in fact, the whole world into the endeavor. So showing what are the science benefits, the technical benefits, even the business benefits or inspirational benefits, benefits for peace as well, going there together of having such a set of infrastructure. And that's why we call it still Moon Village, but in a broader sense than just a little village with little houses on the surface of the moon, but a village in the sense of McLuhan, which say that Earth is a global village where we are all connected, and we should find some opportunities for all inhabitants of Earth. And so that's a vision that we have further developed, and our Director General, Jan Werner, has been a very strong ambassador for this approach. Now, for human base and for Moon Village implementation, there are a number of challenges to get there. So with this, we have good commercial companies that are developing landers, and we will buy the services, but we have to design modules to live, to operate, to survive, of course, and also mobility element to explore around and to exploit resources with humans and robots. And now the new challenge as well is that this will not be only done by government, but by consortia that will involve also private entrepreneurs, funders, investors, maybe for up to 70% of the overall cost of the operation. So now from our place, what can we do to prepare for this habitat? So we had a hands-on approach, also making use of this young professional. We built our own mini moon base at ESTEC. So we developed a small module where I can lock my students for one day, and then they can learn how to live here. I think we could do the same here. We could lock the door of this room at SP and transform it into a moon base and see how we could operate from there. So here you can see some of these astronauts. These are from Superhero, actually. They are communicating with the world. They have data. They can analyze samples. They have a 3D printer, and they have also another lab and rest area. We have also been taking part in a larger campaign. This is the one in the middle of the desert, and that's in fact the Utah desert, where the so-called Mars Desert Research Station that we have used to make simulation where you have a crew for 2 weeks that stay isolated from the world. And there they have their habitat modules, they have a logistic module, the power station, they have also a telescope and a greenhouse to grow plants. So since 2009, oh, sorry, yeah, that's okay. That's a slide. Okay. Yeah. So I have an alter ego trying to hijack my talk. Okay. So yeah. Okay. Yeah. So yeah, actually, this is something that I had recorded for the European Planetary Science Congress, and I should have removed. But in short, it's a program where we perform field laboratory. We test instruments. Also, we have a simulation where we put astronauts, and we can test their performance and how they perform research. What are the issues of an international team? And we use that also as an opportunity to train some of these analog astronauts. Now, for our fellow architect, here is the map of the MDRS floor plan. And this is, you see, there is a lower deck where you have a laboratory, and you have a biology, geology laboratory. You have also a workshop where you can test your instrument and repair them. And you have also a preparation room for extravehicular activity with the airlock. And then on the upper floor, you have the living area with half of it. The hemispheric part is a social area with dining, and also you can do some work there. And you have a separate areas for bed, like bunk beds that are, but you have each astronaut has his own small room. So that's a nice concept, which also fits in terms of size of what you could put in a typical size of a rocket module. So we have also conducted a number of field campaigns. So this to test some of these extravehicular activities, where we had built a lander for the Google and X Prize competition, and we tested how you can use this lander with astronauts or with rovers in a field environment that we have close to Holland in Germany, in the Eiffel volcanic area. So here you can say, oh my God, we have been already to the moon. This, with Photoshop, you can also simulate the partnership between human and robots. Another area, so we are very much interested by the pole of the moon, but also by lava tubes. So these are examples of lava tubes in La Réunion Island, or before we had some that were measured on the moon. And here, this is a gallery in Eiffel that we have explored with extravehicular activities, but also that could be a location where we could build an habitat. And we have a group actually now that is working on this project to build a subsurface laboratory and habitat in some of the lava tubes, including in Iceland. So Mark will talk about that. We have also explored ice caves, and it's possible that on Mars and on the moon, we would have access to ice caves which contain ice, and that could be a repository of resources there to survive. Here, in that case, we first explore an ice cave to take sterilized samples to see if there was life in them, like we would do in the first ice cave we will explore on the Moon and Mars. So this is in the Austrian Alps, huge ice cave, but we expect the Mars and the Moon ice cave to be even bigger because of lower gravity that allows to have bigger structures to be supported. In terms of caves, also we have worked on a project, ILEWG EuroMoonMars, where we had a moon habitat built in a glacier, and with a consortium of more than 25 teams from different universities in Europe, we brought various subsystems, robot, plant growth, we brought our lander, and for example, with the Free University of Amsterdam and ILEWG team, we brought some scientific experiments. We also performed the experiment of isolation in a facility in Poland called Lunares, that is based in a hangar, a military airport hangar, where you can have a full isolation, and such a facility was built, and we have put a series of crew. So this is a picture of the crew before the 2-week simulation. You see all smiling, and we have also a similar picture after. I can guarantee you that they were still smiling from the experience and from the fact that we fed them with plant grown in situ that they could also take care of. So that's not only a dietetic element, also psychological element to having plants there. So in our recent project, we have developed a series of a campaign in Iceland, EuroMoonMars Iceland, and now it's called Chill Ice. So the leaders are Mark and Sabrina and Charlotte, and they are preparing, for instance, a campaign for next year where they are going to place a subsurface habitat in some of these lava tubes in Iceland. Now, recently, in the last 3 years, we have taken the opportunity of a facility that was made available with our collaborator from the International Moon-Based Alliance. It's a dome on Mauna Loa volcano at proximity of the volcanic field where we can test living on the moon. And so I was part of a campaign in 2018 with the owner of this facility, and where we brought some experiments. And then now we are using it as a place where we can conduct moon mission for a duration of 2 weeks. So I returned there in 2019, this time as mission control, so in the comfort of my mission control center, which allows to communicate with astronauts that are sent to the surface of the moon there. So you see, that was our first day there. We had a team, interdisciplinary team of engineers, scientists, even there was a TV reporter, a cook, and that's what this base looked like. So you see, it's really moon-like and very sustainable in terms of energy and operation. And it's in a field of a volcanic field very similar to what you would have on the moon. And so they spent 15 days on this moon base. Some of them, they had problems with the antenna, we had to fix, we had to help them. They prepare for EVA. Some of them are geologists, and they explore the area around, and they discover lava tubes around, and then they come back at the end of the day and rest and enjoy space food that they have to cook their own way. Here I had also 2 geology students, so they made their master research out of this and documented the samples they brought. They discovered new lava tubes. And eventually, actually, we went to visit them with the help of a real cosmonaut, Oleg Artemiev, you can see on the right, and also Hank Rogers, the owner of the Tetris Foundation. So he made a few million with this Tetris game that is investing in green technology and exploration, like running this habitat. We have also the inventor of Tetris on the left. And so it was great to have that. So as a summary, in EuroMoonMars, we try to help to prepare some of this challenge, both for the robotic village, but also for this human basis, by having some studies of a concept, and I'm happy that we are going to discuss some of that here, but also organizing some field simulation in some of this moon Mars habitat to look how to optimize their design, their operation. So one also important aspect is how we can communicate to the public what we learn by this extreme challenge of design in this environment. And so there is a societal aspect, a design aspect, but even we use artists to communicate some of these challenges to the society at large. So that's where I'm going to stop my talk. Thank you very much. Good.
Thank you, Bernard. This was really interesting. And our next speaker is Margit Mischkulnik from the Austrian Federal Ministry for Climate Action, Environment, Energy, Mobility, Innovation and Technology. So you are doing quite a lot, and you are from the Department for Space Affairs. Do you want to do okay, that's fine. So maybe just come this way for the,
No problem.
for the microphone. Okay, thank you.
So I can take off my,
Yeah, so you can take off your mask.
super, thanks a lot. It's a nice, it's a nice slide.
All right.
Thank you very much. Yeah, as you said, our ministry has quite a lot of issues to tackle, and one is space. So I'm from the Space Department. We are around 6 people in the unit, and we also have in Austria a small space agency. There we have, I would say, around 50 people. So in total, we are 20, a little bit more, people who are dealing with space. And as you've heard, it's fascinating, but it's of course also a business. So we have also the private sector, and I will give you a short overview of what we are doing. We have, I would say, 3 different pillars where we are active. So we have the national one, we have the European one, and we have the international one. At the national one, we are responsible for a national support program, and that's implemented by our agency, which is included in the Federal Research Institute, supporting research. At the national angle, we also have our space law. So if somebody wants to start a satellite, you have to register it, and we have to implement therefore this law. At the European level, we have our engagement at the European Union, and we have our membership at the European Space Agency. And what you've heard here, what the ESA is doing, member states can contribute to these programs via signing for special programs, so bringing budget to these programs, and there are obligatory programs, so there you have to pay, and then you have mandatory programs. It's the other way around. The mandatory you have to pay. And where you can choose, Austria was not so active in Moon and Mars and activities like that in the past. But now we see, of course, it's going in this direction. And of course, it's a high potential, the robotic and the human space flight. And therefore, we also contributed to these programs. And we will see, because we have companies, we don't want to bring an astronaut. Not yet, maybe it will come in the years to come. But of course, there are a lot of companies interested in getting techniques and getting their products into this kind of environment. And on the other side, we have the international angle. As you've heard, we have here the UN and the the Space Committee, so we are also active there. And on the national side, I told you we have a national program. So we support our industry and our scientific institutes to get involved and more involved into the space sector. And what we've seen during the years, that it's an important sector. And the sector is growing. And there are more scientific institutes and more companies who are getting involved in this sector. And it's not only that you have the companies that are fixed on space, it's companies coming from different areas. And that's the new thing. You have transport companies, engineering companies, and they are all getting involved in this sector. And we differ between the upstream, so when you go up and you get companies that are involved there, and what's getting important is the downstream sector and the applications. So what can you do with the data? How can you introduce the data in your daily life? How can you use the technology in your daily life? And that's getting more and more important. And we see it at the European level, but also at the international level. At the moment, we are starting to design our new space strategy, because what we are working on is based on a strategy that we have. We have delivered our strategy in 2012, the first time. Now we got an evaluation, and now we're preparing the next phase of our strategy, the strategy until 2023, 2020. How do we say it? 2030? 2030, sorry. Sometimes I get the 2030, sorry for this mistake. And as I said, we also have the upstream sector, but especially also the downstream sector. And everybody is talking about climate change now, and our ministry is responsible for climate action. And there is a huge potential for all these challenges that we have and are facing, and especially this climate area, where you can bring in the space sector and the product, and especially the data, to deliver good monitoring instrument, but maybe also good instruments to grow and to produce something sustainable. So that problems we are facing, and we want to deliver, of course, good products. But maybe you have questions, because you are here to get answers to your questions. So please feel free. I've heard that some of you are studying at the University of Applied Science in Wiener Neustadt, and you are producing small satellites there. And Austria, we have already 5 small satellites built in Austria. So maybe, I don't know, you have questions, because I know you want to build the satellite CLIMB, who can move then and change the orbit, which is extremely interesting. So please feel free to ask all of us, because I think all the 3 others are also here to answer questions. Yes?
Yeah. You have a special program for space startup in Vienna?
We don't have a special program for space startup, but of course it's included in our program. So startups are highly welcome, and if we have startups, but what we have is, in cooperation with ESA, is this ESA the Business Incubating Center. We have one in Wiener Neustadt, and we have the other one in Graz. And there, of course, it's since 2016, we have these incubating centers also in Austria, and they are highly good. And what we are also planning to do is hackathons to get new startups into the business as well. So there will be one hackathon in September, conducted by the ESA BIC in Graz and Wiener Neustadt. There will be another one which is sponsored via Copernicus, so the EU program, and also this one in Graz and Wiener Neustadt is sponsored by Copernicus. And this one will be, I think, because it's implemented by pioneers in October. And then we have another one in November, starting, I think, November. We haven't fixed the date yet. And that's what we are doing from the ministry. So we are also doing a hackathon. And there we have created a close link, because, you know, we are the ministry. There are also companies that belong to the ministry. So it's the railway system, the ÖBB. We have the company dealing with all the highways. It's the ASFINAG. Then we have a company dealing with the flight system. It's the Austrocontrol, and we have a company dealing with the Danube River. So these 4 companies have created challenges. And we want to see how these challenges can be solved via bringing in space technology, space data, and this kind of thing. So there you see, we start to link the space sector with the normal sector, not distinguishing if one is higher or less high. But it's extremely difficult, and I think that's the crucial thing, how you bring the space into the mind of everybody, because what we face the problem when we say, we have a space department in the Ministry of Space and Austria, so it's still in the mind that something very curious, and nobody realized that it's our daily life. And therefore, we try to fix these challenges and bring in these sectors and to bring into the mind and to see, how easy it is that you can solve something also with space technology. Other questions?
Regarding the international theory that you mentioned,
Yeah.
are there any important projects in the future that you are developing with non-European countries?
We are in contact with Israel to build up an MOU. We were involved, you've heard about this Chinese mission. There were also instruments from Austria in it, so we are also having their contacts. And of course, we are extremely linked to Germany and Switzerland, where we also have in our national program, we support projects that are done on both sides so that we cooperate and support the cooperation between these two countries. That's it for the moment. We don't have more yet, but of course we are open to it. And in our national program, we support this kind of international cooperation as well.
In the sense of the support that you mentioned, would it be support for a startup, support for financial budget or for a project, or how is this support shown?
You have to come up with a project. So you have to present a project, and then you have to apply on a special deadline, and then we have a jury, and they are deciding and going through the projects, and then they give a recommendation which kind of project should be supported or not. So it must be a concrete project. Any other questions? If not, then I think my time is over. Thank you very much.
Thank you very much. This was very interesting, especially for me as a fellow Austrian. So maybe one thing I just thought of, if we're having questions from the audience, maybe the speaker can just repeat them, because it's hard to understand with the mask, especially for our guests on Zoom, of course, because the microphone is quite far away. Okay, so our next speaker is actually coming to us from the moon. It is Commander Michaela Musilova from the High Seas Habitat that Bernard Foing has just shown us very shortly in his talk, and she's gonna tell us a bit how the missions there are working. And because she is currently in a simulation, she cannot be with us live, but she sent us a video message, which means I will be doing a bit of a change. We're gonna stop sharing and so Michaela is she's from Slovakia, and she's a geologist actually, but she has been running the High Seas Habitat as the director and also joining a lot of missions as commander. So for my mission, for example, she was my commander as well. And we're going to see if this works. Maybe this might also be a good place for our very short bio break, because this is going to take some time to switch the systems. So if you guys want to get another coffee or just talk amongst yourselves, I'm going to stop this for us. Okay, I think it is time to continue with our next speaker. As I announced, this will be Michaela Musilova coming to us from the moon and telling us about the moon base that she's running together with the International Moon Base Alliance and about all the projects that they are doing there.
Members cannot have a live conversation with anyone. It also makes them have to be more independent in the case of any problems. They are completely reliant on themselves. Remote support can only provide them guidance and advice, but they have to troubleshoot and actually resolve the problems on site alone. Of course, if medical emergency, the simulation can be broken so that the crew members will be provided with the help they need. Though there's always at least one medically trained personnel in the crew, and there's an on-call doctor that can help from everything from minor problems to more severe ones, all the way to managing emergency situations and calling emergency response services. Here are different types of examples of the research research projects that are performed at the high sea station during the different types of analog missions. Some of it is to do with geology and mapping, for instance, of the different lava fields that are present around the habitat. Because the station is located on a volcano, it is surrounded primarily by different lava flows, and you can also find interesting lava tube features. Many of them have been mapped, but there are still a few that need to be mapped in more detail, and that is the subject of a lot of research during the analog missions. You can see some examples of the mapping and data collection from some of the recent missions. Other research projects focus on geochemical sampling and astrobiological studies at high seas, going into lava tubes, as you can see in this picture, and collecting different types of chemical, geochemical, and potentially biochemical samples for astrobiology research. Lava tubes are also studied as a form of potential analog habitats. As you can see from the picture on the bottom right, people could actually fit into some of these very big lava tubes very easily. So these lava tube systems are being mapped and potential habitat structures are being designed to fit inside of them. Different types of research also touch upon the physiological, psychological, and sociological research of crew members during the mission. You can see different examples in these images. In the images on the left, the crew members have been wearing, we call them emotion sweaters, but these are devices that detect the mood of different crew members, and they're used for team bonding activities and to increase empathy between crew members. Other research focuses just on the influence of regular exercise on the mood of the crew members and their general well-being, and you can see some examples of that in the pictures on the right. We also do a lot of different types of technology testing, especially things related to in-situ resource utilization, but we also have access to different types of rovers and drones, as you can see in this image. Some of them are in collaboration with organizations directly here in Hawaii, for instance, the organization Pisces, which lent us the big one where you can see the image on the top left. And since we have to do so much engineering work, we have at least one designated crew member that's an engineer, and they have to maintain all of these different systems and equipment, write daily reports, and troubleshoot any problems with the mission control. The different missions at high seas include the EMIS missions, which are the EuroMoonMars, IMA, International Moon-Based Alliance, and high seas missions. They are involved with many educational and outreach projects. Here are some examples. On the bottom right picture, you can see me with a research project designed by high school students in Slovakia, which was focused on using human hair as fertilizer to grow crops on future space missions. And then various types of documentary films were filmed here, including a recent film called Space Truck, trying to make people understand the importance of space exploration and how it might be relevant to all of us on Earth one day. And finally, all of the research data and findings from the missions at high seas are being gathered to build a prototype moon base here in Hawaii in preparation for the building of a real moon base on the moon one day, which we're hoping will be an international collaboration and an interdisciplinary one, which is why we encourage a variety of types of research projects to take place at high seas. We'd like to acknowledge all the many crew members of the different missions that took part at high seas. There are too many to put on these slides, so a big general thank you to all of them for everything they have done for this facility and for research, space research in general. Here's some references for more information about some of the research projects that we've been doing at high seas. And if you'd like any more information, here are my contact details and some social media information where I post also recent pictures and reports from missions, including the one that I'm currently on right now. So thank you very much for your attention, and greetings from the moon. Aloha.
Well, a big thank you to Michaela. we're going to send her a few pictures of today. And also I can really highly recommend that you follow her on her Instagram channel or Facebook page that she just showed the link to, because she's always keeping people up to date what's happening on the moon mission. So you can be live there and hear what's happening on the various missions. This is really interesting if you want to know about how those missions proceed and what they're daily doing, cool pictures from the lava tubes.
Excellent. So if you have a question for Michaela, you could also send her. And through the time machine, maybe we have an answer.
Exactly. I could send her a text message, but I do think she's asleep right now because of the time difference. So we will have to see.
But any question for Michaela or about Anthony? In any case, yeah, we are looking for volunteers for the next expedition. We are still online. Yes,
we are still online.
Yes.
Yes.
So we have been planning a mission, EMIS mission at the end of this year. Because of COVID, we had to separate it because only Americans have now access to the Hawaii. But we are looking for volunteers for next year. And so if you're interested, please contact Michaela or Sabrina or me, and we can also involve you in the preparation of the next campaign. Yeah.
Are there any requisites or any requirements for these volunteers?
Yeah. Actually, these are volunteers. We could say these are candidates, astronaut analog, and they go through various training. And we are looking at people that have already like a research project, some good incentive to go there, also good physical conditions for this mid-altitude, 2,500 meters, and EVA. And also there is a financial contribution that we ask from the analog astronaut for being there, even if we co-sponsor some of the cost. And we are also interested to have them part of an institution or possibly sponsored by an institution so that we can continue in a sustainable way to organize this campaign. Otherwise, we organize also some preparation activities for other campaigns that we do in Europe. Excellent. So now it's my pleasure to introduce the next speaker. The next speaker is Sabrina Kerber, and she's a very good collaborator for our cause. Not only she's a space architect here, educated in TU Vienna, but also she has been joining our EuroMoonMars team as an analog astronaut, spending time 2 weeks on the surface of the moon in this moon base in ICES. But also now she's coordinating such activities like this space habitation workshop. And she's our communication manager. Also, she has been running some TV channel, web show, YouTube channels for EuroMoonMars. So Sabrina, the floor is yours.
Thank you very much, Bernard. And I'm going to start my presentation now. All right, so now we have heard what's happening on analog basis. I think it's time to go closer to what else we can do to improve the life in space habitats during space missions. And those are also some projects that we are researching during these analog missions. So what I'm presenting you is how we can use additive manufacturing in space architecture, and a project that I did together with EuroMoonMars and MakerBot during the MS2 mission. So Bernard already said I'm working with EuroMoonMars on analog missions and communications. I'm also finishing my master thesis at TU Vienna at the moment, and I have recently founded a startup, X-Planeta Space Solutions, with a few collaborators in Vienna. And what we are focusing on is to come up with smart solutions to improve habitability in space habitats. And much of this revolves around using additive manufacturing. So first of all, as communications manager, please do follow our EuroMoonMars on social media with the handle @EuroMoonMars. You can find us on LinkedIn, Instagram, and Facebook. And we also have a Facebook page group that everybody can join and put in discussions. It's called Space Moon Mars. So you're very welcome to come and also share your own projects on that site. It's a really nice way to exchange with each other. You can also follow my startup Explaneta on LinkedIn and Instagram with @Explaneta. We're trying to be more active there and bringing you the news, what's going on, but I'm just going to tell you about it. So how is additive manufacturing used in space architecture? How do we use additive manufacturing in space habitats? First of all, and maybe a good start to our workshop, what is space architecture? This is a question that I get asked on almost a daily basis. So it's defined as the theory and practice of designing and building inhabited environments in and for outer space. So pretty much everything that's away from Earth, space stations, extraterrestrial habitats, spacecrafts, but also launch centers on Earth or analog habitats like HISEAS or the one that we're trying to build in Iceland that Mark will be telling you about in a bit. So this whole space architecture involves two factors. It is really important to keep an eye on the technical aspects, so enabling us to create something where humans can live, but making it possible for us to live somewhere is not enough. This does not mean just because we can breathe there, because we have a pressurized environment, that humans can actually survive there. We also need a keen eye on habitability and human factors, which means we have to make sure that the space is actually worth living in. And this is a really important factor of space architecture. Additive manufacturing can be used for both of these aspects. And I'm gonna explain to you the three approaches that we mainly use additive manufacturing in. So the first one is modeling. This is pretty straightforward. I'm sure it's the first one you thought about. So creating nice models is a very, very time-consuming and also very, very expensive thing in architecture, and maybe not the favorite thing of us architecture students, but it is highly useful, not only to show maybe your client or your peers the dimensions of your habitat, but also to yourself get a feeling for what your habitat is going to be like. And additive manufacturing is really, really nice for that, because we can just scale our models, we can add details, we can change things in the process of designing and then quickly reprint it. So we can have nice draft models. Draft models are usually very, very ugly looking, and you would like cut things off and stick new things on. And in the end, you don't have anything really representative. But when you have a 3D printer, you can very quickly present a new model that people can actually relate to. And also for presentation models in the end, you can see, as here done by a colleague of mine, an absolutely stunning model of a space station. So with additive manufacturing, we can just create much, much higher results. Then I think one of the most important approaches is in situ engineering and human factor applications in a small scale. So if you fly to the moon, for example, and you have a mission there, you're probably gonna forget something on Earth, because you always forget something when you, for example, go on vacation. You're also gonna break things, and problems are gonna occur that you did not foresee. So what do? You would have to call Earth to send you, for example, a new tool. This is incredibly expensive, incredibly inconvenient. So it's not a good solution, especially when you're on Mars. It's not even a solution. For Moon, you could do it in a emergency situation, but as I said, it's also incredibly expensive. However, if you have a 3D printer, you can simply print your tool. You can also adapt that tool to the problem. So you can see here on the ISS, for example, they printed a screwdriver as one of the research projects they did there. But maybe this screwdriver does not work for the problem because it was a problem that you did not foresee having. So you can quickly on the computer adapt the model of the tool and reprint the tool to your specific needs. So in general, always when we send something to space, we have to mind payload efficiency. We have to send up really, really small and lightweight components. Being able to send up lightweight filament and then printing whatever we need on site is not only for the engineering aspects, but also for the human factors and crew psychology, a really good approach. Because everything I just said about tools also applies to personal objects, to leisure time items. So if you're on a long-term mission and you can only bring 2 personal objects with you, you're very quickly going to get sick of those objects. But with 3D printing, you have the opportunity to even recycle those objects and reuse maybe old packaging material from food packages. So one of the problems is that they create a lot of waste. So the astronauts, after having eaten their food, they have a lot of waste where the food was packaged in. And so NASA and ESA are currently developing really cool technologies to recycle these packaging materials, these plastic waste components, to create filament from it. And then we can print, for example, leisure time items or tools. There is, however, another approach to using 3D printing in space architecture, and this is in situ resource utilization. So we can use resources that we find, for example, on the moon or on the Mars, to create habitats. So this image is from Foster and Partners, the moon base for the Moon Village idea, and they have used the regolith, so the lunar soil, to create the radiation shielding for a habitat. And this is a very, very common approach nowadays. So you can see here, this outer shell is all made from regolith, and they have done a bunch of studies on the structure. This is the structure that they came up with, and they're not printing it with a conventional gantry system, so they don't have one big 3D printer that moves its arm, because of course it's a huge base, and you would have to send up this huge printer, which again would be very inefficient in terms of payload. They have come up with a system of these tiny little robots. So they're starting up with just a couple, and then they can send up more if they want to increase the base. And those robots are at the same time gathering the regolith and bringing it on site, and then printing it in a sintering approach. So it's a very, very smart approach. You can see here between 1 and 3 meters of regolith is enough to shield the inhabitants inside the habitat, depending on where they are on the moon and what angle the sunlight and the radiation hits the habitat. So for this base, I think they have gone with a meter of regolith shielding on top and 3 meters on the side. So during the MS2 mission, so at the high sea space that Michaela just presented to us, I did a project with the company MakerBot. This is an additive manufacturing company. They are building 3D printers. And I was there in a 2-week lunar simulation. And one of our research focuses was on space architecture and additive manufacturing. I think I can quickly skip this slide because Michaela has made such a beautiful introduction. But just in general, yes, we get 8 minutes of shower time per week. If we want to leave the habitat, we have to wear a spacesuit with a life support system. We have to work out at least 1 hour per day. We have to eat only this dehydrated food that you can see. And it's in general very, very confined and very limited access to tools and leisure time objects. We did have great tools there, but it was just the stuff that was there and nothing else. We couldn't improve on the tools that we had there. And this was my goal, was to improve the situation during the mission, not through really good planning before the mission. So thanks to the company MakerBot, I was able to bring a 3D printer to the moon. It was the MakerBot method machine, so a pretty big system actually. Yeah, and I set it up in the engineering bay of High Seas and started printing after a few challenges with the altitude and also with delivering such a system to the moon. But once it was up and running, we very quickly experienced great benefits of it. So what did I print? For example, for the engineering side of things, I printed a tool to build a small rover that our chief of engineering was building, and we realized that we didn't have one very simple tool, tweezers, because nobody had thought to bring that, and it had gotten lost in the high seas toolbox. So this was not a simulation. We actually did not have tweezers, and tweezers are actually something super easy to print. So just in I think 2 hours, we printed a pair of tweezers that she then used to connect the cables for the rover. We also printed a part for our mission drone that we also did not foresee needing, and then just had a really quick fix. You can see here in the picture on the right, I was preparing the print. So the printer itself was set up in the engineering bay, but I could monitor it from my workstation in the main habitat, which was a very convenient feature because it gets really cold in the night in the engineering bay. So I was really glad I didn't have to spend hours and hours in there, but could sit at my comfortable workstation. We also printed items for habitability, so personal items, leisure time objects. I allowed each crew member to select one personal item, something that they could not bring to the moon, but missed or would like to have after being there a week. They realized, oh, this might be something that I need, and I think it really, really helped us to break the monotony, but mostly it was really important for crew bonding, because just the act of choosing an object and then printing it, getting the object, and people were going super crazy, running up to each other like, look what I have. And so it brought really like a great amount of joy to the habitat just to have a different tiny object. And those weren't any big things. It was like really small toys or really like small tools, pots for the plants that one of our scientists was growing. So we tried to integrate the researches with each other. But overall, this was a very successful study, and I hope to be working more on this in the future. As a few examples of how else we can use maybe the in situ example that I mentioned before, how we can use additive manufacturing. So this is a project from the Moon Village design that I did, I think, 2 years ago. This is about the base that was set in the side of the craters in caves, and we use additive manufacturing to sinter the interior surfaces of the caves, because you couldn't just leave them bare. You have to create a pressure bladder and also have a divide between the inhabitants and the lunar rock, because this could be really dangerous. So we use 3D printing to make the caves habitable. And another example is from my thesis, actually. So this is a inflatable habitat. It does not work that much with 3D printing in the general structure. Instead, we have, as you can see here, in the middle, a rigid module, and then this is all inflatable technology that will only on site be inflated, so that we have an efficient payload, and then on the moon the interior fitting is going to happen, and this is where additive manufacturing comes in. So not so much for the shielding, even though this also uses a cover of regolith shielding, but not 3D printed. But the interior fittings, many of them are 3D printed on site. So as you can see, we have here those applications are all 3D printed. Maybe a short explanations for the non-architects. So in a moon base, our ceiling height has to be very high. So you couldn't do with a 2.50 meter ceiling in most of the spaces, because you would bounce and hit your head the way we usually move. So in most of the rooms, we have to have very high ceilings. But there is also certain rooms like the hygiene units, which is the example here. On the toilet, you don't bounce around, you go in there, sit down, and then you leave again. So we're able to have, I would say, normal ceiling heights here, and this creates the possibility for example, storage, as I did here. And the good thing on the moon is places that are up high and seem very out of reach are super easily reachable. So you could just pull yourself up with one hand and just grab the things. But of course, to increase the safety, I have added a handhold and also this deployable footstep. And as I said, they are all 3D printed, so we only have to ship the filament, or we can recycle filament, and especially if we want to change something about the base, it can be super efficient. So maybe just a quick introduction to end this presentation about what my startup is doing. So we are coming up with smart solutions to improve the habitability aspects. As I said, we're really focusing on using additive manufacturing for this. We're also using deployable and inflatable technologies, and those are really nice integratable with additive manufacturing components. We also have a really keen eye on sustainability, because it's also something that works super well with additive manufacturing. And we're using a collaborative approach. We have space biologists from the Netherlands, for example, supporting our current project. So we're working on 2 projects at the moment. One is GreenCase, a mini portable greenhouse, and the other one is Gravity Act, on which we're working with medical experts, which is a training tool for 1/6 and 1/3 gravity, because this is something you can't really prepare for on Earth. So when you get to the moon, you will need to quickly adapt, and we want to create a tool that can be printed and adapted to the astronauts and then be used on site really quickly. So this is the GreenCase. It's about, I think, like that size. And so in general, this is not to have tomatoes or strawberries to feed the crew, because it's, of course, way too small. This is a habitability topic. Greenery and plants have really, really big benefits on crew psychology, on breaking the monotony. The astronauts actually experience them as little pets. They take care of them, and the GreenCase should enable the astronauts to take care of the plants, to bring them with them. This is a dock system, so you can either dock it in your crew quarter, maybe like on your nightstand, you have like a lamp, but instead you have the GreenCase. But you can also bring it with you on long rover journeys. So for example, in the Moon Village, when you would transfer from one base to the other, this could take several days in a rover, and you could bring this and also dock it. It's working with a aeroponic system, so it's not soil-based, it's very lightweight, and we're aiming to have almost 100% of the system 3D printed. And yeah, as you can see, it's currently under construction and under prototyping, but we're very excited about it. Thank you very much for listening to my talk. If you have any questions, just shout them out. I will repeat them for Zoom. No questions?
Great way to have a synergy between your passion, or also starting this business with new partners, and bringing for the first time this big equipment for 3D printing halfway to the moon. That was quite impressive. So any questions from our audience? Also for you that are on the YouTube chat, you are welcome also to put some questions that we can address to the speakers overall later. Yeah. So actually about X-Planeta, do you have also some projects where you found some good terrestrial application, where you could have also some funding partners that can join, or like installing space habitat in the middle of a city, or have you?
Yes, we're also pretty much aiming for that. Currently, we are only working on the 2 projects that I have showed you, because it's a very new startup. We're just in the founding and funding progress at the moment. But yes, we are also aiming for bigger things, especially with the background of space architecture, designing and maybe deploying habitats on Earth as a prototype testing would be very interesting. We are also planning to test our prototypes from the projects that I have just shown you, although we're still working on how to do that with the gravity devices, because of course we do not have the lunar gravity on Earth.
I think it's a very very nice also to have our members from the ministry listening to this very innovative approach. And I'm sure your ministry will be interested. Also, our ministry about environment, and also maybe also interested. I had the pleasure to meet the minister, or the new minister of environment in Alba a few weeks ago. And I think that, yes, there is a quite a good innovative climate, but also good challenge that climate gives to us to develop a solution. So now we move to the next talk.
Our next speaker is Roxana Perrier and Sonia Pavi, and maybe Bernard, you would be the better man to introduce them.
I'm sorry, I have a question.
Yeah, sure.
Your presentation is really good.
Thank you.
It offers groundbreaking or space-breaking opportunities. But in your opinion, are there any challenges right now 3D printing bases that will need some improvement for this?
So for our Zoom listeners, the question was, are there any challenges that 3D printing is facing and for the space application? And yes, definitely. I think the technology itself is a bit challenged at the moment still, especially for the big scale projects that I showed, like 3D printing with lunar regolith. This is a technology that is still under development, and although there have been amazing steps in the last couple of years, there's still a long way to go, because as I have mentioned, it does require either really, really new solutions or huge systems that we have to launch to the moon or worse, even to Mars. So I think this is one of the main challenges at the moment.
Okay. So it's my pleasure to introduce. So we have our two speakers from IPSA Toulouse. So Professor Roxana Perrier and Sonia Pavi, and they are going to report on an exercise where they have been conducting, in particular with some students over the summer, about IPSA space habitat studies. So I have met Roxana actually last year when she was one of the co-organizers of a big banning festival about the moon. And she has also brought together a large team of students from IPSA, Toulouse and Paris, and they are going to contribute to some of our EuroMoonMars activities, including spending 1 week in a moon base in October. And so the floor is yours, Roxana and Sonia. Thank you.
Okay, I'll try to speak loud so we're not getting too close. We need to keep a baby elephant in between us. We told us so. I'll try, yeah. So thank you very much for inviting us. We are very lucky to be here. I know that in this context it's very difficult to get from place to another in Europe, but yeah, we're very happy to be here. We will present our space habitat concept as much as we could advance this summer in parallel to their internships, because they were in summer internships. So we will start by introducing ourselves, and I'll leave.
Yes, so I'm going to start by introducing Mrs. Perrier. So she did a Master of Science in Chemistry. She has a research doctorate in organometallic catalysis. And right now she's a teacher of space science and physics at IPSA. And she's really passionate about space exploration, science popularization, and education.
And of course, just by me, here's Sonia Pavi. She's a third-year student in aerospace engineering school, so at IPSA Toulouse. She's collaborating with me and helping me to coordinate all the working groups with EuroMoonMars collaborations. So since this June 2020, and of course for her future, she would like to major in space launcher and satellite. But for now, we will try to present you how did we get here. So at IPSA, our education is of course based on science, technology, engineering and mathematics. That's a basic lectures, tutorials, and practical working, of course, but we will try to lean on project-based learning. And what we propose to our students is it's choosing of their first 2 years of preparatory classes, one of the big projects that go for 1 or 2 years. Among these projects, you have 5 examples. We have a 6th that joined us this year on simulator with a glider. But what happened this year in June 2020, that's how we met EuroMoonMars and Bernard Foing, is because he honored us with his presence for the final presentations of the blog. So, ILEWG it means to the open sky. So there are articles about space and aeronautics, interviews with experts. We have a big project about a telescope. That means designing, constructing, programming a telescope that will be installed in French Polynesia and will be remotely piloted from Toulouse by our students. Wind tunnel and digital experiments, of course, because we're talking about aeronautics, but not only, even space passionate students can do it, because you have to know, in order to get to space, we have to go through the air. Space experiments that I have the chance to supervise is a big project about prototypes, experiments that we can send in the future to space. We start by applying to a zero-G contest opened by the French Space Agency. So we have a concept of space spinner, that's a space station that will spin, and thanks to the inertial force, you will feel as either 6 times lighter, either a third of the gravity. And as you know, we have a lot of satellites and telescopes in space, a lot of data coming from space to Earth, and we need to interpret them and treat them. So for that, we have passions about algorithms and informatics that joined in a big project about space data. And you have there, Give Me Some Space. It's a collaborative platform on which they will talk about it, and they will join in order to treat all these big projects. So data. So this big project allowed us to have a lot of competences, especially the students, and they invested these competences in the next generation. Had that
Yes.
Sonia will present.
So we worked over the summer with the IPSA Habitat Group, which is supervised by Professor Perrier here. So inside of it, there are 6 students who are first and second year of engineering school. So there's me, Sonia Pavi, Mathieu Lafont, Audrey Moritz, Sébastien Lebec, Quentin Brou, and Theo Podolski, who worked on this project over the summer. So now the first step we are going to have for our habitat will be going to the moon, sorry. So from now, and ever since 50 years ago, with the first Apollo moon, the only manned spacecraft we used were mostly low Earth orbit, and now we are going to try and go and inhabit the moon. So there are a lot of new issues that we will have to think about, and we'll have to try and solve them.
So, how do we get to the moon? First, we need to choose a launcher. We looked at the market, and of course, we chose the one that's most affordable. What does it mean? That we will look at the price. So the most affordable is the Falcon Heavy SpaceX launcher. We need the launcher because we need to think about how big will be our habitat, our module. So we saw the fairing measurements, and we thought about a 2-module spacecraft. A first module that will be the transfer module, and the second one, the habitat module. Inside.
And what we're thinking for the first mission, we will have a crew of 2 to 4. Sorry, we will have a crew of 2 to 4 people, and the mission duration will be 15 days, with our area of settlement being the South Pole, which is enlightened 200 days a year. So we are going to talk about later why we chose this one. Our basic concept will be this type of habitat with a diameter of 5 meters and the height at the highest point of 5 meters too, so that we have a living space of about 65 cubic meters. So that we think that will be enough for the beginning. And we want our materials to be aluminum and carbon. And we will also use a thermic shield, just like the EV1, which is inflatable to protect our habitat.
As for the power supply, we will take the one that's the most practical in the solar system. We will take solar radiation, and of course, solar panel technology, because it's the one that's most known, proven, and recognized. We took the solar panel of the ISS as an example because, as mentioned yesterday, May 2001 was where we installed the last solar panel on the ISS, and that allowed the International Space Station to be declared as completely inhabitable for the mankind. So this way we'll have 20 years next year of continuous manned mission in low orbit. So once we choose the solar panels, you have to know also that Moon Village concept talked about already about the solar panel farms. We choose to join that to hydrogen fuel cells. It's another technology that was proven and chosen already ever since the shuttle missions. So we thought about joining these two types of energy together in order to provide with energy our moon habitat.
So now for the protection, we are going to use an anti-projectile shield, which will be the Whipple shield type because of its weight. It's really lightweight. It offers a good protection and it allows us to combine the efficiency of several materials. We are also going to add some regolith. So we are here, we have the inside of the moon habitat, sorry, the structure, our shield that we just presented. We'd had a frame that we would cover with smart fabric and fill it out with regolith in order to protect it even more from the harsh condition in the moon.
So now, of course, when we have the protection, we will think about the inhabitability inside. As proven by the last 60 years of manned missions in space, the water consumption is generally of 4 liters per day per astronaut, and we would have to consider the fact that we produce carbon dioxide. As all of you can see nowadays, having carbon dioxide concentrated around our mouth is kind of uncomfortable. So that, as we produce it, we have to use it. So we are considering a Sabatier reaction that will change carbon dioxide and hydrogen into water and methane. So that's useful. Help them grow as future engineers, and why not the next step and the future going to the moon. Thank you all. Yeah, I don't know. Sorry. We don't have our presentation anymore on the.
Yeah.
I don't know what happened. We don't have it anymore.
That's okay.
It's okay, it was just the thank you slide.
Here. Okay. Well, thank you. And maybe are there any questions from the audience? Then I'm going to repeat them into the microphone. Yes. Sorry? How thick is the shielding? So how thick is the shielding?
Which one?
Which one?
All of it. Sonia, would you like to answer?
I don't remember exactly how thick it is.
So I think Sabrina mentioned it. We would need a protection that would go between 1 and 3 meters. So yeah, we will try to dimension that in order for the inhabitants to be protected and safe.
And what is the time scale that you see for the project? So how long would the astronauts live in there? Because obviously on the moon, they can't, even with the best protection, they can't be there much longer than 6 months. So do you plan to really use those 6 months or?
So for now, we really focused on the first mission we want to do, which would have a duration of only 15 days. So it will be, yeah, it will be short. It's only to make sure that everything is fine, there's no problem. And then we plan on adding other things to our habitats and try to have a longer mission. So yeah, up to 6 months, we thought would be a good idea.
Okay, great, thank you. Any more questions? Okay, I think then we can move on to our next speaker. We can have a tiny bio break. Yeah. We are running a bit late and we have already had our break. But yeah, let's have a tiny break just for those who need a bio break.
Okay, maybe let's entertain our YouTube viewers though.
Yes.
So if there are some questions from YouTube viewers.
I have checked YouTube and so far we have no questions.
We have received a number of comments from YouTube.
But we have some comments.
Viewers, a lot of support for the IPSA effort. Go IPSA and MPOL. What else? Good luck IPSA from Audrey. T1 pod 1, pod 2 with that?
Yeah.
Good luck, Sonia and Madame Perrier.
Okay.
Okay, so we have a good remote support team.
Yes, we do. Thank you.
Okay. Okay.
All right.
Good. So.
I'm just quickly gonna.
Yes, so yes, hello our YouTube audience. As I mentioned, you are welcome to post some of your questions on the chat, and we try to address them. Yeah. So now, yes, we have our next astronaut is now preparing himself. He's currently in the airlock, ready to intervene on stage. Yes. So yes, you can do. So it's my pleasure to introduce here Mark Heemskerk. So I've met Mark Heemskerk at the Free University Amsterdam, where he has been working on his bachelor and master in geoscience. In particular, he was an active coordinator and participant in a campaign that we have performed last year in the frame of the ESA Igluna adventure, where that's a project where we have a federation of universities contributing to a space project, but from a student perspective to learn, to train. And he was then a co-coordinator of the contribution from Free University of Amsterdam, so coordinating a team of about 15 colleagues in bringing scientific instrument to a moon base that was installed in a glacier in Switzerland. But he has also performed his research project on testing the properties of moon Mars analog simulants to see if we can use them to build structure and habitats. And he has been also a key leader in some of our pilot projects and now real projects, which is to organize a moon habitat and a laboratory in the subsurface in a lava tube in Iceland. And so he has done a number of scouting campaigns there. He will report on that. And they have found also nice names for this project. Chill Ice. The floor is yours, Mark.
Okay, thank you, Bernard. I hope everybody can hear me. As Bernard already introduced, I will tell a little bit about our project called Chill Ice. And Chill Ice stands for the construction of a habitat inside a lunar analog lava tube. Indeed, I can remove my mask. Everybody is far away from me now. And of course, it's the Iceland campaign of EuroMoonMars, and the final version will take place May next year. So the objectives of our mission, in very brief bullet points, we have discovered suitable lava tubes both on Earth and on Moon Mars. And we conducted studies on the settlement habitability. So can we indeed move into a lava tube, whether it be on Earth and hopefully in the future as well on the Moon and Mars. So we are scouting for habitat design suitable for lava tubes, and we are focusing on international collaborations. And the one sentence goal of the Chill Ice mission is to build a habitat inside a lava tube in 8 hours or less. But why do we want to go into the subsurface? It, of course, also brings extra problems with us. We need to, even in the very simplest story, we will need to bring at least a ladder to safely descend into.
Ik weet niet wat ik heb gedaan, maar ineens heb ik een heel klein windowtje. Dan krijg ik hem nou weer groot.
See if I can mute. Yes, that's better. Okay. So why do we want to go into the subsurface? And this is mainly to do with the transportation, and especially the transportation of protection. So even a relatively small and relatively unprotected habitat, space habitat, such as the International Space Station, already weighs over 400,000 kilograms. And you do need the protection. You need to protect yourself from the radiation, but you also want to insulate yourself. Especially on the moon, this can be a major problem where you have almost 380 degrees Celsius change between the lunar day and lunar night. And especially for lighter metal alloys, this can be very fatal eventually in the long term. But you also need to protect yourself from the regolith. This is the very fine-grained dust that you can find on the moon and on Mars. And of course, you can use it for in-situ research utilization, but you don't want to use it in the lungs of the astronaut. It is carcinogenic, and it will eventually also kill the astronauts. And then there's also the problem of micrometeorites. These are tiny specks of dust, but they are traveling with insanely high speeds, and they also can destroy the habitat. So you need a very strong and rigid structure to protect yourself from this. But as I said, a rigid structure for just a very small amount of people like the ISS weighs over 400,000 kilograms. And if you calculate that each kilogram to the moon costs nowadays around 1 million euros per kilogram, it's going to be a very, very expensive habitat. So that's why we want to use the structures that are locally available, such as the lava tubes that we have. These structures can provide all the protection that you would need simply by going inside there. And the temperature inside is constant. And another cool thing, especially for me as a scientist, it is a pristine environment. It has not been changed and it has not been altered by radiation. There's no regolith inside. You will be safe from the micrometeorites. So the crystals and the minerals that you find on the inside are exactly the way they were since they were formed, which is 3 billion, maybe 4.5 billion years ago, which can give a very unique insight into the history of our solar system, and with that also the Earth. So you can see a tiny skylight or an opening into a lava tube on the moon here. This is an Oceanus Procellarum. So in terms of efficiency and safety, but also in short time readiness and research, I think it's crucial that we need to at least look into lava tubes as habitation. And this is what a lava tube looks like on the inside, at least the lava tube here on Earth. But we also have lava tubes on Mars. So this is on the western side of Alba Mons. You can see the big Alba Ptera, and this nice publication done in 2019, which identified several lava tubes. And as you can see, there are literally hundreds of them, or expected to be hundreds of them on Mars. But also on the moon, again, this is on Oceanus Procellarium. So that's the big black blotch here on the left side of the moon, which contains at least 80 lava tubes and has over 300 skylights already. So there is enough opening to actually go in there. But where do we want to go? And where did we go already? So we had an ice preparation mission, which was the sort of scouting mission in Iceland that we did in 2018, in which we identified multiple lava tubes which might be suitable. And eventually we settled on one. And then in 2019, as Bernard already said, we had the Igluna test bench. This was the pilot project of the ESA lab. Then earlier this year, we had the scout mission. We went back to the lava tube we picked out during the preparation mission. And we took all kinds of measurements in terms of height, in length, and in width of the cave. And then eventually for next year, we have chill ice planned. And hopefully, if everything goes well, and let's assume it does, we will also host a permanent habitat, analog habitat in the future. And this is a short picture. So the Chill Ice core team, some of us are available and present here. So Bernard Font, I think you have seen him. He's our mission advisor. I'm the geologist on the team, and I'm in charge of the subsurface operations. We have Charlotte Pauwels. She is head of logistics, physicist from the Netherlands. We have Sabrina, space architect, who will help us with the design of the habitat. We have Evelyn Downs from Ireland, who's a radio physicist. We have Tom van Rentegem, he's from IPSA, and he will also support in the engineering. And we have also my brother here. He is our remote support and robot engineer. So where do we want to go? We want to go to the moon, of course. But first we need to go to Iceland, and we are going here in Stefánshellir, which is a cave system together with Surtshellir in the lava flow of Hallmundarhraun, which of course everybody knows. It's in the western part of Iceland, and this is a very nice step that has been made in the 70s by G.R. Reich. And as you can see, I'm not sure if you can see my pointer here, I don't think so. I will just point it out, here is the large gallery where we will build our habitat. You can also see it in the profile. It's about 60 meters deep. It's most part, it's over 5 meters high, and it's about 7.5 to 13.5 meters wide. And this is what it looks like from the inside. You can see a little pile of rubble here in the forefront, and we will build our habitat in between where the photo here is taken and the pile that you can see there. Just to give a bit more impression of where we are. This is an aerial picture taken by a member of parliament who flew over by plane, and you can see just above there a bunch of black holes, which are the openings into the lava tube. And on the right, you can see the actual opening. You can also see that there's some ice inside. And we actually hope that there is also going to be some ice on the moon and on Mars. Although for our eventual mission, it might also be a problem if the cave fills up with ice and then we have to dig ourselves in. So for the Chill Ice mission, we have a few days of preparation on site, which probably will also consist of digging out the ice into the tunnel. And of course, we will also prepare our analogs, which will probably be in the same few days. And then we will have a short simulation. It's going to be only 36 hours just to give a proof of concept that it is feasible that astronauts can live in there. And of course, afterwards, we will focus on the outreach and information exchange. And the wrap up, we need to make sure that everything leaves the cave that we also placed in there, just to keep the environment clean. And of course, we will also focus on the national outreach and publications of research results. And as I said, if everything goes well, we will continue with a more permanent space analog habitat, and this will be in cooperation with local Icelandic teams. So, in brief statements, Chill Ice, the mission, we will focus on exploration. Of course, we will explore lava tubes, but for this, we will also need new technologies to see how we can safely descend and deploy habitats inside. With that, of course, comes a strong focus on human well-being, not only on the moon and on Mars, but also on Earth. And of course, we want to prepare for settlements later on so that we can actually go into the solar system and explore. So our slogan is from into the Earth to into the universe. And if you want to follow EuroMoonMars or the Chill Ice project, you can always come in contact with us. Are there any questions? Questions from the audience? Maybe questions in the Zoom? I think we have time for one short question.
You are all welcome to join in the campaign, but also remotely. We'd love to have also some links with Vienna when we are going to do this campaign. Maybe we could organize some also with ESPI as a remote support center or in Russia.
Yeah. Okay. Thank you. I will close this.
Okay, thank you very much, Mark. Seems to have been very clear and no questions. And coming up next is another Heemskerk brother. So Mark's brother Robert is going to talk about his part in the MES3 mission and the robotic experiments that they did there. And of course, the robotic counterparts to us humans are also really important for space habitation. So we need robots to set up the habitats, but also to run and maintain them. And I'm curious to hear what you have to say about that.
Thank you for your introduction.
Excellent. So I think no presentation. So it has been a pleasure to work with a robot with experience in robotics and actics and tele-operation of a robotic system that he has even been able to test on the real moon by going in the places on Mauna Loa, where you have a very similar landscape and properties that you will encounter on the moon. So, yes, Robert, the floor is yours.
Thank you for your introductions. So, hi all, I'm Robert, and I will tell you a bit about my work at the MES missions, indeed on rovers, especially on rover cooperation. So a short introduction to me. I'm a student in mechanical engineering in Delft in the Netherlands, focusing on telerobotics. During my MES mission, my main research was on rovers, but there were also a lot of other research like psychological reviews, research, and also physiological a bit more. So my research was with 3 rovers. The REM rover, sponsored by EuroMoonMars. It's the one on the left. It is quite small and has 2 tracks, 2 caterpillar tracks. The Helelani is the second rover, sponsored by Pisces. That's a quite big one, about a golf cart in size. And then the third one is the Zebro, which stands for zesbenige rover. It means 6-legged robot. And as you can see, it has 6 legs, completely different driving mechanism than the other 2. So a bit more specifics on these rovers. The Helelani rover by Pisces has been used together with NASA and Honeybee Robotics in an experiment called Planetary Lego. And this research focused on issue utilization of the of the resources to build a landing platform for rockets that would be arriving on the moon or on the Martian surface. So it could prepare the ground, and even in the picture on the right, with a robotic arm could lay the tiles that are made from the lunar surface regolith, or actually in this one an analog regolith, to make this landing platform, and they tested it with an actual rocket on top of it. The Zebra is the six-legged robot is actually a swarm robot, but they aim to launch only one test model in 2022, actually to the moon, where they will test all systems if they work, before they would put them in a swarm with a lot of these tiny robots all together. And in this way, you can explore new areas faster than you could with one big rover. And if one would break down or get stuck, it's not the worst. And actually, the others could maybe help and get one out. And together, they can also even lift objects if they are made for this. And also for communications, this would really work, because communications only work in a direct line, and if they're this small and they cannot reach a satellite, if there would be any even on the moon, then you could relay the communications through each rover and go very deep into, for example, a lava tunnel to explore what is in there. The other rover, sponsored by EuroMoonMars, was bought mostly for comparison to the others. So it has a robot arm, and what could this add as in manipulative tasks? There's a gimbal camera, so it can actually look around and not only look forward as the others two only could. So to see if that is really something necessary for robots to look around and not only look forward. We also wanted to compare the tracks, if this would work better than legs or than wheels. And it's actually just a toy rover, so it's very cheap, very small, easy to assemble. And the others have spent years to design these rovers, maybe spent years to build them. And this is just a toy rover you could assemble in a few hours. Well, ask the engineer of MS2. So what I did, I tested some individual abilities, like these inclinations, how steep these could go, but also some objects, if they could cross over, for example, bigger rocks, or that they would flip on their back. And I also did some, what you can see with this is, for example, that you can see here the Zebra rover, and it has only one camera, very low to the ground. So this would be most of the time what you would see. You would only see the tiny rocks that would be in front of you. And it could climb rocks that are as big as itself. But if you cannot see over it, you don't know where you're going. So that's why I tested also cooperative scenarios. So with this one, I have two rovers deployed. On the left, you can see the Ram rover, and on the right, the Zebra rover, and they can film each other. And with this, you could see more than the rover itself could see. So I hosted a remote event where I deployed all three rovers, and all three were remotely operated from different places in the world. Actually, only one was operated from inside the habitat without any direct visual view. and the other two were operated from the Netherlands, one in The Hague and one in Delft. And through the camera that was from all rovers, I streamed the camera to all other operators. And in this way, they could climb more obstacles and they could not run over each other, as one is way bigger than the other two, but it cannot see directly under its wheels. So that's why they had the cameras also of the others, like, where are you? Oh, I should not move back. If you want to have some more results, I can give you them later, but I think I want to conclude for now and say thanks again to all the sponsors for making this this mission possible, and also my personal sponsors. And of course, a big thanks to the EMI's crew that really made this not only an educational but also a really fun experience to be in isolation before it was cool. Thanks. Are there any questions? Yes, please.
I enjoyed your presentation very much.
Thanks.
Thank you for it. And I wanted to ask if the rovers can be also, if they're only controlled by the humans, or can they be controlled by themselves? I don't know how to ask that, but can they be automatic? Can they think for themselves, or when they are in a swarm? So how can they interact with each other? And
yeah. So the question was if the rovers are only remotely controlled, or that they also have some automation in it. The Helelani rover, the big one, that was used in the planetary Lego experiment, was partially autonomous. So it could drive around and could do some manipulation tasks on its own, but not fully. The RAM rover is only remotely controlled, does not have any AI behind it or any autonomy. The Zebra rover, the one I took, I only used it in remote control. There is also a possibility to use it in a more autonomous mode, and even in a swarm mode that's also autonomous. So not only the rover itself, but the whole swarm would react autonomously.
So actually on this question, I have a comment and I come here. Is that actually, that's true, a very good question about autonomy of robots. So we have been also involved in other collaboration, in particular with the DLR group that has conducted a series of campaign with really autonomous rovers. And we have done a simulation campaign in Etna in 2017, and we do another one next year in June 2021 with 3 rovers, 2 of them completely autonomous, 1 teleoperated by an astronaut, and they will do a test how they can perform some experiments in the Etna as an analog of the moon. So please keep in touch for this ROBEX campaign.
Thanks.
And also, if you want to ask a question via YouTube or Zoom, we are constantly checking and getting really nice comments back from you. Thank you, but feel free to also ask us any questions, ask the presenters. We will keep checking and answering your questions. I think for now, we have another 2 presentations before lunch. And the first one will be by a group from the FH Wiener Neustadt. So guys, if you want to come up. And you are presenting a satellite project that was done for FH Wiener Neustadt. And maybe I can ask you just to give a bit of an information about yourself and the team as well. Is your presentation on it, or you can talk?
So hi everyone, my name is Pruch Munlo. I'm an aerospace graduate and alumni of from the University of Applied Science of Wiener Neustadt. So today I'm going to present to you on behalf of my team our CubeSat project. So first, you guys are wondering what is a CubeSat. So a CubeSat is basically a small nano satellite, and as the name suggests, it looks like a cube. So each unit is 10 by 10 by 10 centimeter. Okay, so yes. So where is our university located? For those of you who are not from Austria, so it's located in 40 kilometers south of Vienna. It's called Wien Neustadt, and the university has approximately 3,500 students. The engineering department was established in the year 2012. Our first CubeSat project started in 2014. It's called Pegasus. So this is how it looks like. It's a 2U CubeSat. And it was launched in June 2017, and it's still operational in orbit. The university is very well equipped. We have all the necessary facilities to develop and qualify nanosatellites. Such facilities can be shown in these pictures. We have the additive manufacturing facility. We have the vibration test facility, shock table, thermal vacuum chamber, solar simulator, Helmholtz cage, and outgassing facilities. So for more information of our CubeSat program, you can visit the first link. And if you would like to know about the activities of Pegasus, you can visit the second link shown below. A quick introduction to our mission. So our mission is the mission of the CubeSat. Our mission is to go to the lower region of the Van Allen belt, which is shown in the picture. It's a region of highly energetic charged particles due to solar wind. And as a space engineer, you normally want to avoid that region, but we love challenges and we want to go there. About our mission objectives, firstly is education. So students can get hands-on experience and knowledge on how to develop nanosatellites from scratch. And secondly is technology demonstration. So some of the components that are used on the satellite are off-the-shelf components. So we have to make sure that these components can withstand the harsh environment in the Van Allen belt. And as a technology demonstration, we are using electric propulsion to steer, to maneuver our satellite. And it's used especially for this low-cost budget mission. And last but not least, science. We would like to conduct scientific measurements, such as radiation and magnetic field measurements at the Van Allen belt. Coming to the duration of a mission, the first phase one is the launch and early operation, which takes approximately less than a month. Then moving on to phase two, when the satellite starts moving to the Van Allen belt, which takes 12 to 15 months. Then the phase three, which is conducting of scientific measurements, which takes approximately 6 months. Then we have the thruster to deorbit the satellite, which takes around 9 months. To give you an overview how a satellite looked like, it's a 3U CubeSat. So we start off with the communication system, which consists of Stacy D, Stacy S, and the antenna unit. We have OBC, which is called onboard computer, which is the brain of the satellite. We have PSU, power supply unit, which consists of PPU, power processing unit, solar array, and battery unit. Then we have the thruster for maneuvering, and we have the rails to support the structure of our satellite. Some challenges that we faced during our project, but before I dive into it, I would like to inform the audience that the majority of the components that we use on Climb are flight heritage or have already been flown in space. So these components are in Pegasus, basically. And some of the critical components from off-the-shelf components are basically the ADCS, Additive Determination Control System, and the thruster. So we realized that the power generator in the satellite is less than expected. So we tried to mitigate it by reducing the duration of its operation time in space. And we found out that the mass budget exceeds the allowable limit. So we try to optimize the CubeSat structure so to reduce the mass as low as possible. We can also have delay in the shipping of these products, or even sudden unavailability of these products. So we have to plan in advance and order these components in advance as well. And of course, we do not have enough manpower. We don't have enough students. So, but in order to mitigate it, we try to advertise our project so that it can reach as many students as possible. And we have overlapping responsibilities. As for example, myself, I was responsible for design, simulation, testing, and manufacturing of CubeSat components. And last but not least, the most crucial part of our project is funding. We do not have sufficient funding. So to mitigate it, we try to apply for additional fundings in advance, and we have a very accurate cost management. So you guys are wondering how can CubeSat be used in space exploration? So ANSAR is a good example. It's a space mission study that I had the chance to be part of. It was a project from my course. It's called Space Mission Analysis and Design. So the mission objective of ANSAR is basically to send a fleet of CubeSats so that these CubeSats can detect solar storm and relay information in advance to the spacecraft that are carrying crew members from Earth to Mars so that they can seek shelter if necessary. So as you can see in the video, there's the sun in the middle. The blue orbit is basically the Earth orbit, and the red orbit is the Mars orbit. So as I start the video, a fleet of CubeSats will be deployed from Earth, as shown now. So ANSAR is basically the fleet of CubeSats. And after a period of time, each CubeSat will orbit to its respective orbit. And after a certain amount of time, the spacecraft will be launched from Earth. So now the CubeSat is at its respective orbit. And after a few seconds, the spacecraft will be launched. Yes, so the spacecraft is launched, the purple orbit. And when the satellite reaches the purple region of the orbit, they will start detecting solar winds and yeah, if you want to answer.
I'm allowed to answer to the question. Right now, the project is to create this project plan, and according to the success that we had with Pegasus. So the question was if there are any plans of creating a series of similar projects to this, and the answer is yes. Right now, we've been very successful with Pegasus. It's a satellite, like my partner mentioned. That has been flowing for about 2 years roughly, still existent, still providing communication data. So that is very, causes a lot of good energy to create more of this. And according to the product and climb, I think we can create more projects up to come. So if this project is successful, I think we have enough funding, enough students, and well, enough energy to go on and see whether we can create something further out on the scope of our project. Thank you.
Thank you for your attention.
Okay, thank you very much. So we only have one last talk before lunchtime, and I know we're all hungry and eager for a break, but this one is actually a very special talk. It's an online talk from Poland. Bernard, maybe you want to do the introduction?
Thank you. So hello. It's a pleasure to have with us Agata Kolodziejczyk. She is a researcher and from Poland, but I had the pleasure to meet her when she was working at ESTEC, at the Open Space Research and Technology Center, as a postdoctoral researcher in our advanced concept team. And actually, we had some very interesting projects together, including the preparation of lunar habitat that she developed with some colleagues, and we participated to a campaign that took place in 2017, a series of campaigns in this so-called lunares habitat. And we had even collaboration how to grow plants in a moon soil, and we made a specific work on that. But now she has installed a new moon-based habitat in Poland, near Krakow. It's called Solberg Moon Habitat. And she has developed a series of activities like an astronaut training center and the possibility to live in such a moon habitat in isolation. And we planned to perform some campaign there in October. So Agata, it's a pleasure to have you with us, and the floor is yours. Thank you.
Good afternoon, everyone. Can you hear me loud and clear? Good afternoon.
Yes, we can hear you.
Oh, you can hear me now. Thank you. Yes, I have a big challenge now because you are very hungry, and I will try to make it as short as possible. Can I share my screen and my presentation?
Yes, you can share your screen. It's enabled, so just press the red button below. Yeah, exactly.
Okay, let's start. So you see my slide now, yes? Can you see the slide?
Yes, we can see the slide. I just have to keep going on unmute here.
Okay, great. So welcome everyone one more time. It's a pleasure and great honor to be with you, with my heart in Vienna. I really love the city, and I'm so happy that I could join this amazing meeting. So I represent Analog Astronaut Training Center, and today I would like to tell you briefly about analog missions in Poland. Why we are doing this? First of all, you all know that since last time we had only one capsule lifting people into space. It was a Soyuz capsule for 3 people, and now we have built a new capsules, very nice, very fancy, like Orion capsule for 4 astronauts. And here you see 2 capsules, one produced by SpaceX for 7 people, and the second one or third one, the Boeing Starliner. What it means? It means that soon every one of us can go into space, can be an astronaut. So also conditions changed. You see, this is the photo from the Soyuz capsule, and now this is the photo from Dragon capsule. Look how fancy it starts to be, like a Star Trek conditions or Dreamliner conditions. So it is really, really cool. And soon I hope we will be there. What is not a dream, what is a real? We are all looking forward into seeing the Gateway, the new platform to study deep space environment. And this is the fact. Europe is also involved in this project, and we are very happy to think about it, that this is real, this is not a science fiction. And of course, we are trying all to discover, to develop technologies, to develop new knowledge, how to live on the moon and then on Mars. And this is, for example, the project of our student. We together, he made his master thesis collaborating with our private company, and he created this kind of project. So, of course, we are inspired by what happens on ISS, International Space Station, and we can see that nearly 90% of life, of astronaut life there in space, is inside. So it's not only EVA, which is, of course, the most fancy thing and all people dream about EVAs, but in fact, EVAs are only tiny percent of work during the mission. And therefore, we focus on inside. We created habitat to test most of things inside. And we want to make this inside work safe. This is one thing, and efficient. This is the second thing. Because, you know, living in isolation is not easy thing. So we are working particularly on health issues, how to protect people living in isolation, to stay healthy, to protect their microbiomes, their biodiversity. That is very important and critical for sustainable health in isolation. Then we are focused in our studies on time perception, because we know that this is also important in motivating people living in isolation. So time perception is also very important, and of course, motivation. So our training center starts preparing analog missions from the beginning, so from the training to the mission. And here you can see one of our AITC person. This is my partner, Matt, and he's now in parabolic flight here on this photo, testing some, processes in the brain. Then we train our analog astronauts in Poland on the human centrifuge. We have very good equipment, one of the fanciest one. There are 3 such human centrifuges in the world. And we try to profile Soyuz capsule flight start, the launch and landing. So all these kind of forces, G-forces, acting on your body, we test on our astronauts, analog astronauts, of course. And this is how we observe also physiological parameters during this Soyuz profiling. We also train our analog astronauts in a hypobaric environment. And here you can see Matt and the analog astronaut. She and he, they are now fixing some tests to see what is their level of oxygen in the brain. So these kind of issues we train. We believe that you cannot really think about space, living in space as an analog as an astronaut, without building your own rocket. Per aspera ad astra. Aspera are like rockets, yes? You cannot go into the space without a rocket. So we train all our people how to build a rocket. And then these rockets are not only models that, that they have all aerodynamic parameters correct, but they really fly. Here you can see. Yeah, exactly. So they fly. We also try to design new parachutes, not only for rocket landings, safer rocket landings, but for safe balloon landings. And here I'm testing some parachute for balloon stratospheric missions. We also train our analog astronauts in preparing stratospheric missions. So not 100 kilometers above the land, but 30 kilometers above the land. And here you can see we, together with analog astronauts, we launch the balloon mission, and it looks more or less like this. It doesn't make some noise, but it's different. And it is also very important experience that all analog astronauts, I believe they should think of before going to the analog mission. Okay, and now we launch. Yeah, so you see, we launch rockets, we launch balloons, then we of course analyze data, and our goal is always to publish the data. So we are not only training people to trying to show them how big problems they have to think of when they want to go to space and think about space, but also we want to prepare them to be creative and to find out something useful for people, not only for them, for their excitement, the experience, but also for science, for other people. What we do also, we train people in the air, land, and water trainings, and these are all kinds of stresses that first we want to administrate to them and then observe which one is good to be an analog astronaut, which one is not. And I must say that then we thought about building a habitat base, but not the same like we are in other countries. We tried to build a laboratory, so not only to run analog simulations, but also to run real science. And we are very happy now. We celebrate now 20 missions for 2020. So this is what we already organized. And during this whole time, we built in total 3 habitats. EMPOL mission, so all people who are going to Poland in October, you will have your workshop. So the next MoonMars workshop will be in this building that you can see on this slide. Can I see a cursor? No, I can't show you, but you see the main building. This will be the conference building on site, which is the private observatory, astronomical observatory in south of Poland. This is like a jungle in Poland, so you can see so many stars because there is no EM pollution in this area. So I hope we will have a nice sky and we will make a beautiful observations in this site. When it comes to analog simulations, we of course select analog astronaut crews and mission control center crew. And here you can see on the left our happy analog astronauts and then our happy mission control center crew. But because of so many missions that we are now running, so our habitat has no single day, free day, so we cannot clean it. All maintenance has to be done by analog astronauts. So each crew has to prepare the habitat for the next crew and there is no break. So because of this, we have habitat operational system. This is like a board computer controlling all missions. So I'm the only one in Mission Control Center that I can handle everything. On request, we can invite capsule communicators. For example, we will have a Mina Takla from Egypt, sorry, who will be a capsule communicator for Destiny mission in the future in the October also. And again, our goal is to build, to train people and to make science. And this is some of our results from analog simulations. For example, cardiorespiratory profiling during simulated lunar mission using pneumography. This was part of PhD studies of my friend Marcel Młynczak. Then, of course, I told you we are trying to work on motivation in isolation, and a part of motivation is time perception. We also publish in this area. So we try to make this kind of studies, and this is the habitat that EMPOL 1 and EMPOL 2 crews will meet, I hope soon. We work on lighting system. This is my own project. So we developed a special lighting prototype to control all sunlight spectrum in the habitat. And also my partner, Matt Harasimchuk, that I showed you in parabolic flights before on the slide, he prepared fantastic sensory control of the habitat. So we have more than 50 sensors inside the habitat to monitor all data, what happens inside. Another project which we are doing is to collect physiological data, not that analog astronauts will have to do several times during the day, what is now happening, but we want to design a special system to monitor not only the habitat, but also analog astronauts. So everything will be remotely, will be excluding human errors, you know. This is one thing that it's standing behind this idea. And this is one of t-shirts that we were testing already without sensors, but with nanocellulose. These brown things are kombucha nanocellulose parts. We can obtain many things out of kombucha. Kombucha is a consortium that is growing in our habitat. You will see how it looks like, and I hope you will make something useful out of this nanocellulose. We, of course, publish a lot of things now with this cellulose because this is one of our analog mission project, one of the main one. So how to design, how to optimize production of nanocellulose in the habitat conditions, for example, growing only on algae bioreactors, not on tea and sugar. And we are soon releasing our our book, origami book out of kombucha. This will be some hybrid with space and kombucha. I hope you will like it. And of course, we are analyzing all types of systems for hydroponics, aquaponics, and so on. Here we have all types of regoliths, different medias, different seeds from different countries, even from different continents. Now we will test seeds from Africa, from Zambia. So I'm very interested what will be the result. And that's all for now. If you have questions, of course, I am very open to answer. Thank you for your attention and welcome for collaboration because we love to collaborate.
Thank you very much, Agatha. Are there any questions from the audience here?
It's amazing how, in parallel to really working out the logistics of running an habitat, you have a very research-oriented approach where you try to, you perform experiments and you publish them so that they can be shared with the community at large. So my question is now, yeah, for running really the operation, so you say that you have what type of personnel do you have in terms of mission control and far remote support?
You say what kind of communication we have?
No, so how many people do you need to really run this facility with remote support? So you have, I understand you have 6 inside the current habitat, and outside, how many do you have?
Yes, so now I'm the only one, but because of my all kinds of problems that happened recently, I had to ask Matt to help me. Yes. Because we have to collect samples every week during the mission. So we have to ride from Krakow to the habitat. Okay. We call it a trapeze of lander. And of course, we perform all procedures that analog astronauts do not have any contact with us, but they have to open the airlock and we deliver them the dry ice. Then they have to put their samples on dry ice and then we take it back. So this is what we have to do. We have to operate the habitat and collecting the samples. This can be done by one person, but we have to have a nurse collecting their blood samples. You know, because of policy, they cannot do this by themselves. So in the beginning of the mission and at the end of the mission, we have to have a nurse, another person. Of course, we have a remotely working medical doctor. So we are always able to contact him in case of problems, as well as psychiatrists. So we collaborate with experts in order to have, if we have some problems, we have to consult these problems with experts. So basically now I counted 4 people.
Okay, excellent. So that you have been able to organize the logistics of remote control with the technologies that, in fact, you have only a few working, and so you have a kind of autonomous habitat. So that could be also valid for Mars operation. But of course, for this medical experiment, you need to have access to samples. I think that's amazing. We are looking forward
and for us,
to come. Yeah.
Sorry, Bernard. And for us, this is very important because then we can reduce price for everything. Then mission costs are really cheap because if they require very low, amount of people. So this is a real reduction of costs.
Super. Any other questions? And from our audio YouTube, if you have questions on the chat, we can also after convey them.
Okay, I think for now we are ready for our lunch break. So to our viewers on YouTube, we will put on a short break. We will be back in like 40 minutes, so 13:40. We will continue with an afternoon of design concepts for lunar and Martian bases, and also approach the subject of how we will handle society and culture once we are in a space habitat. Thank you very much.
Ja,没什么事。
All right. Welcome back to the Space Habitation Workshop. We just had a really nice break with a huge lunch. And we're going into an afternoon of space design now. We're starting with a group from TU Vienna, from the space architecture team, that are presenting a design or a concept design that they made for the idea of the moon village. And it is actually a moving habitat. And with us today is Götze Yilmaz. Hi, Götze. You can unmute yourself and activate the screen share now.
Hello. Hello to everyone. I'm Götze Yilmaz, and like Sabrina said, I will be presenting a project we did in 2018 with my colleagues Güneş Aydar and Emirhan Veyseloğlu. We designed a mobile habitat for moon exploration. Our idea or our concept was that we want to be scouts, so we're going to be mobile. How can we use our mobility? We can use our mobility as infrastructure. So rather than bringing the supplies to us, we can go to the supply stations. If there's a water station, we can go there. We can go pick up the astronauts. And we also created a pattern to always stay under the lunar sun to utilize the solar energy as much as possible. So for our scenario, we imagined that there will be a water gathering outpost in South Pole near the Malapart mountain, and our first mission would be exploring the South Pole Aitken Basin. When we first thought of staying under the sun, we thought of a circular path, but a circular path is not very flexible. So we decided to opt for an elliptical path, which is much shorter. And if we were to turn this path around the South Pole or around our water gathering outpost, we can explore a large portion of the southern hemisphere. We did a rough simulation of how fast we have to go, how long do we need. We don't want to go very fast for the habitat and the people inside, and also for the laboratory. So average speed for us was 10,000 kilometers per hour, and we have approximately 6,000 kilometers to go. So we will need 28 days to finish a cycle, which is exactly the same as a lunar cycle. And we're going to have 5 days to stop for EVAs, or if there's a problem, or if we have to stop for a while. So our path is around the South Pole Aitken Basin, and the promising research spots stay inside of it. And to collect samples from these areas, we also thought of having smaller rovers, which we can deploy from one side of our path, and while we're going back, we can collect the rovers. So we're gonna have 2 Falcon payloads. First, we're gonna send our legs, our cranes, which can be folded. And at the next step, we are gonna be sending our habitat, and then we attach the habitat to the cranes or the legs. We have in total 30 square meter solar panels and 48-hour emergency energy storage. And the wheel system is inspired by Rooker Buggy system of Curiosity rover. And the living space, the interior is of course very limited. We thought it for 3 astronauts, and we wanted to have as much separation as possible. So we thought of the end of the habitat as a working space and the front of it as recreational for sleeping and for eating. And the hygiene is in the middle like a tampon. You can also close the working area if you want to. And at the very end, we have the EVA space. The sleeping area is also surrounded by the water tank, which can provide an additional radiation protection while the astronauts are sleeping. It can be used separately for 3 people, or they can use it together, for example, to watch a movie. The laboratory has a retractable shelf system for having different missions, at different times. And the EVA part is with seat parts and glow box to have as much as possible outside dust inside. And we have our special design is that we wanted to have at the sleeping areas windows which are opening, and then they have mirrors so that astronauts can daydream or watch outside when they want to have a private time inside the sleeping areas. And also the backside is taught for the rovers. When the door opens, the rovers can also go up there for bringing things, or if we have to change some parts. Yes, thank you.
Thank you very much, Götze. And thanks for being able to join us online today. Are there any questions from the audience? Yes, I can just relay it.
So I think there were only 3 people in the vehicle. What about the psychological research behind this? Do you know how long they will not wear each other?
Did you hear that in Zoom or?
Yes, I hear. So the one cycle is 28 days. So let's say 1 month. We thought they would have 3 cycles every mission, so 3 months tops. They would stay together, and like I said, we also plan to have an outpost. So if there was a problem or they want to change, of course they can go to the outpost and change the people.
Thank you. Yes, we have another question, maybe.
I was wondering, how do you deal with any spare parts? I can imagine if you're traveling with relatively high speeds over lunar terrain, that your wheels might break down, and if you cannot drive, you might miss your sun. How do you mitigate?
We want to travel with 10 kilometers per hour. Did I say it wrong? We don't want to go so fast. If we have a problem, of course, we're going to have to repair. We have 5 days of extra time during the cycle if we have to stop. So we're going to have to do it in 5 days then, or we're going to go back to the outpost to have repairs.
And is it also possible to dock to other bases of the Moon Village to get repairs if it's not in your schedule?
Yeah, this would be an extra design. We also thought maybe if we could have a better village structure, these shuttles could also be used for transportation between the bases of the Moon Village. But this is a further thing that we have to do. We didn't actually work on that.
Okay, thank you. Are there any more questions? If not, then we're moving on to our next team, which is again a design team from TU Vienna, and they're with us here today in live mode. It's Shil Schneider and Armin Ramovic, and they will be presenting about this year's design studio on Mars. You have it on here already?
All right, thank you for having us. Hello, everybody. My name's Jill. This is my project partner, Armin. And we will present to you today our project that we did last summer term at the TU Vienna. It was part of a design studio called Mars Science City and was led by Sandra Holpig-Meusburger. And it's called Moving Mars. So part of the task was to envision the future of the space travel and space habitation. That's like the first part that we're talking about today. And the second thing is like to go more into detail how to have like a feasible project that we could that would be feasible to do. So let's start with our project called Moving Mars. And let's go like this. Let's talk about the vision first. We are thinking about a future where we can move free in space, in outer space, like from planet to planet and from galaxy to galaxy. This will be in about 1,000 years from now. And from that aspect, we broke down to a more feasible idea, moving Mars, where we had a closer look into some projects of big thinkers like Buckminster Fuller or Jonah Friedman, Leo Tian-Boulay in architecture that were dealing with spherical forms or circular forms, which are perfect to move around, because we were like, okay, we want to have something that is movable. We don't want to build a city, but we want to have like a connection between the different cities that will be up on Mars. Different space agency will be there, that will build their cities. We want to be the connection between them, either for cargo or for people. So we work with round-shaped spheres to move people and cargo around. So that's also why we had like a look at the city, the walking city of Archigram, which is also dealing with moving cities. So regarding the design studio, at this map of Mars, you can see a lot of different cities. These are the cities that other students this semester planned in their project. And we are like the little white dots in between that are our villages, our little spots where you can check in and then move on the routes that are connecting the different cities with our rover that we are presenting. And now I'm heading over to Armin.
Hi. So this is the first look at our rover. This is how it looks like, and I'll explain you a few slides how it works also and why does it look like this. First of all, you see it looks like a ball with an arm in front of it. So the arm is for interacting with the surroundings and scanning the surrounding and interacting with the Martian soil. This is how the rover looks like opened. So first image you saw, it's the rover is closed, and this is the opened and stage. Like he can move in either way, like closed or open. The sides, the white sides, are the modules that can be exchanged and can be used for different functions. They have different functions, so they can transport people or cargo or something else. We used a method, origami method, where you can connect to different triangles, and these modules can be folded and unfolded. So deployed, and this is how it looks from this is the top view and the plan view of the rover. So on the left side, you see the docking to the villages, to the city. And the middle one is when it's moving and it has the modules on the side. And the right one is when you just need to transport the people, the astronauts on the Mars, and just move faster. So we wanted to have a smaller and to travel faster and lighter.
So here you can see a schematic sketch of the rover. So it's a top view. On the left-hand side, you see the rover. It has its deployable unfolded, and it's docked onto the docking station from the Martian habitat. And when it's docked on this docking station, the fuel cells of the rover are fueled up with energy. And also the rover is being pressurized so that when you're on the rover, you don't need to wear any spacesuits or anything like that. And in that moment, when it's docked to the docking station, you can also ship in the different modules that you want to take with you. So in the next picture, you can see a section of the rover. On the left and the right-hand side, you can see some examples what you can take with you. So you can take either with food and plants, or like stuff that you need for experimenting on the Martian soil, or you can take people with you. And on the middle part of it, it's the cockpit. There's all the functional stuff that you need the rover to function so that it drives around. And on the top, you also have the possibility to unfold some solar panels on it. So when you're in a research mission, you might need some more extra power. So you don't run out of power, you can unfold them. On this slide, you can see on the right-hand side 3 different modes that the rover's wings can be in. So that are like the white parts. The first one is traveling mode. So you have the inner part and the wings right on top of them. You just roll around it so you can move quite fast. If you want to take some stuff with you, some cargo with you, you might want to inflate the unfoldables. So the wings need to go away and make space for them. They fold up, and then you can unfold the unfoldables and drive around. And if you want to stop somewhere on the Martian soil, you might need to get some more grip. You just turn the wings around and they get more grip. You can think of it like an insect. It moves like this then, or can stand in one position. So, and these 3 different types of the wings that can move around, it gives you the opportunity to operate on uneven ground or perform on rough terrain, as well as, like I said, getting into static position and also find grip to explore in like caves or something like this to have a better grip on the ground. And just to make sure, the orange parts are the parts that are moving. That's only the wings are moving here. The red parts are like the static parts. They won't move around. So if you're inside the foldable, you won't be feeling like being in a washing machine or something. They will be static, and only the wings are rotating. And here's another image, an isometric view of an example of which modules you might want to take with you if you're going on a research mission. So on the left-hand side, you see a module equipped with a cooking space, a space for socializing, a space for sleeping. And on the right-hand side, you might want to take a laboratory with you with equipment for small experiments and so on, so that you can go on a spacewalk, take some things that you want to examine, take them with you inside, and do your experiments on it.
So we'll look at some scenarios, how the rover would be used and the usability of it. So on this image, we see the rover is closed and it's just driving around the Mars, scanning and interacting with it. Also, because we have these wings, the rover can move in different ways and on different ground. So it can operate on rough terrain. On these images, you can see the rover that's docking to the to this one module. It's coming to this docking station, opening the wings and expanding the modules on the side, so it can then transfer different materials you need, cargo or people or something. This is then the traveling mode, where you can take with you what you need on your mission, or if you just travel from one spot to the other. So you can go out of the rover on the backside. You have these solar panels that are above and that can expand to fuel up a bit and use
use for the mission, use the electricity for the mission. The astronauts can go out and then do the go on a spacewalk. We'll take a look at the village because we also had to build a habitat, plan a habitat for it. We thought about building these stations that are between these cities on Mars. The colleagues did. So the white round dots are our pit stops or stations where the rovers can interact with each other, they can charge or take a break from everything. So we plan on, first of all, connecting a few, then in a few years the others, and then after a few 100 years we can connect all the Mars, so we'll be the main transport company. So our pit stops we plan on doing them like this. So on number 1, we have a landing site. Number 2, the power facilities, and number 3, there is our village that can expand. We planned on having these modules, this blueprint of it, that are transported to Mars, that are inflated. So we have the central living unit where the astronauts would and people would live, and the outer space is for working, and there is this racking system that can be used for the cargo or anything you need to transport, inside of the these modules. Then they are connected with this with that airlocks you see, and also on the sides are the docking system for the rover. This is the section. You see the inflatable modules, and over it the 3D printed shell. It needs to protect the building for radiation and space debris. And this is an image rendering of how it would look like on one location, for example. So you've seen behind the modules underneath this shell, and our rovers just going around this station.
So we're going to have a short look at the timeline. We will start around 2044 to build the inner parts of the inflatables here on Earth and ship them with some rockets up to Mars, and then they will inflate themselves up there. And if everything goes well, we will have more rockets going up and slowly forming a village up on Mars. And if still everything is fine, we will start printing the shell that's gonna protect the village from radiation and send up the first humans with the first rovers. And then shortly we'll try to build up these different villages up there, having more people up, and start to connect the bigger cities from the space agencies that will be up on Mars. And yeah, that will be around 2056, we think, that we will start doing this service. And to finish up, here we have some pictures of the projects that some other teams did this semester on this project. They built a city, and we wanted to show our rover how it cooperates with their city. So it goes to their city, taking people with them, bringing cargo to them. And if you're more interested in more of these projects, you can go to issuu.com/Hochbau2, and there you'll find some booklets of previous semesters that worked on similar issues. This semester's booklet will be out soon, I hope. And here's the last render of our city. So this is Moving Mars. Thank you for your attention. Any questions?
So, I have a question. First,
I think there was a question before, sorry. So my first question, you said they are inflatable modules?
The stations are the inflatable modules, but the rover is it's deployable. It's static parts that are deployed, unfolded, and so on. But the living parts, so the station, is inflated. Yeah.
Okay, so I understand that they can inflate on the vacuum, but where do you get the air from the astronauts?
If I get you correctly, you're asking how do we deploy those things? Yeah, they can only be deployed when being at the station, at the docking system. That's where they are going to be pressurized, and then they roll up like this to the next city. If you want to unfold them back or deploy them on your way, that won't be possible yet.
Thank you.
My question was, according to the modules, it can be used for cargo or passengers. Are those modules completely exchangeable, or are those modules fixed, and you have one compartment for cargo, one compartment for people?
Do we have a slide for it? Yeah. They're not interchangeable, but if we go. Well, if you look at maybe this one, so here you can see the modules connect. There's a door that opens up, and then they can interchange the inside of the module. So the outside, the deployable part is fixed, but the inside can be interchanged.
Great design.
Thank you.
Okay, thank you very much. Our next speaker is Borghildur from Iceland. However, I think she's not in the Zoom chat at the moment, so we will just have to be flexible, and we will first talk about science and culture and art with Eva Petric, who is with us in the room. Eva, if I can ask you to come to stage. And I think Bernard is going to introduce you.
Yes, okay. So it's a pleasure to have with us Eva Petric. So she's Austrian-Slovenian artist. And I've met her actually at the European Geoscience Union a few years ago when she was the first artist in residence to represent art in this big assembly where there were more than 8,000 geoscientists. So she was there, one artist for 8,000 geoscientists, and she had some installations there. And we discussed some joint projects there. And we had the pleasure to have a visit where she came to our Space Research and Technology Center at ESTEC. Even she performed some experiment with our EuroMoonMars team. We locked her as well in our moon base for part of a day. And she could explore also what you feel when you are isolated on the moon. We even had some paper that was presented at Europlanet and other events at LPSC as well. And so we have started this collaboration between art, space, and geoscience. And she has been also developing a number of artworks she will describe, and in particular, some work that she wants to send to the moon together with our Moon Gallery project, where we want to send a gallery of art to the surface of the moon. So Eva, the floor is yours.
So thank you so much for the nice introduction, and thank you to all of you for your wonderful and inspiring presentations. I feel a little out of place because I always feel that being an artist, even though I also finished psychology at university, I'm a little bit like floating above, and everybody else is like very concrete and on the ground with all the science, you know, because you as scientists, you always have to, you have the pressure of showing that your thoughts can really be real, and you have to prove all the time. As artists, we don't have this pressure. So I always take science and facts as an inspiration and challenge for my artwork, and I always try to look at things from the other side. And it's been an inspiration to work with Bernard and also other scientists. I had the experience to go to CERN, and I always like to include so opinions of scientists and their thoughts and also their feelings in my work. And I guess why I'm here is to present a concrete project. It's called the DBE, Data Bank of Emotions. And it's a kind of hybrid between an actual kind of commercial work, artwork, and scientific experiment. You can see it here, and you're welcome to come and also apply it on yourself and see if it, like my aim was, if it teleports you to what Earth represents to us, our home. And the final product you see here is actually a collaboration between me and another industrial designer, Mateja Šušteršić-Dimitz. And how this started, it actually started as an idea. As Bernard mentioned, I was part of the moon simulation where I was designated with experiencing isolation at ESTEC in 2015. And after this interesting experience, where I really, I had to feel that I'm deserted on the moon by myself, and really write down my experiences and feelings, and also time perception. How did I feel that time is passing? And it actually passed for me much slower. So this was interesting. And after that experience and the paper we wrote together with Bernard and also the collaborator Irene Schlacht, which was presented also at the Cosmology Conference in Nantes and was part of the Harvard EDU. For this paper, they told me, come up with 2 art projects that would go into outer space, change in the context of outer space, and the mission would be to keep astronauts connected with Earth, and it would protect against alienation, like feeling of loneliness and isolation. So I thought, okay, well, I went and dug into my art, and for me, I always work with emotions because as a human species, I think what's unique to us is emotions. We know actually very little about them, but they're an essential part of us. And emotions are like fragrance, they're ephemeral, but they can teleport you to different modes of existence in an instant. So I thought, if I can come up with a fragrance that gives feelings of Earth, it conjures up in astronauts associations to home, this can be the fastest way to combat feelings of isolation. And the second project was the Earthling mark, stem cell tattoo. And the idea was to, as you see this figure, half white, half black, it's a translation of one of my shadow photographs into lace, that this would be tattooed on the skin of an astronaut. So it would physically change in the context of space because our body changes there. But also it would, be a marker reminding astronauts of how they are interconnected within themselves, their body, and other humans and the Earth. Because in the end, we are, a fabric, we're all interconnected. It's just like the dark matter. We don't see everything. But in the end, one string breaks, everything resonates. So it's called DBE, Data Bank of Emotions, a message from Earth. And each bottle is a unique hand engraving of one of my shadow photographs translated into lace and then hand engraved. And the top is made by Mateja Šušteršić, and it alludes, to an asteroid. So this was part of also the mission in Hawaii that Mark was heading. And I remember I was writing up a whole protocol, so it put me back in my years of psychology. And I was thinking, I'm giving you such a hard time, and all the participants, what you have to do. But thank you for including it in your daily program. and also incorporating it into your geological studies and spraying on the soil, which will also be part of the Moon Gallery exhibition and one of the 100 pieces that goes to the moon in year 22. So I'm excited about that. And as I mentioned, fragrance is for me a kind of magic. Scientists, engineers are trying to also incorporate it and bring it into the virtual reality. And as of now, this is still impossible. I would say thanks God, because it shows that we as a human are a physical species and we are part of the physical environment, and we can't deny that. So to show you a bit of the background, I'm fascinated by shadows because, of course, they are not present without a physical entity. And everybody has shadows, also objects. So in a way, they are equalizers, social equalizers. And I tried, I was borrowing the periodic table of elements, which for me is fascinating. It summarizes all of physical existence. And I tried to translate it into the ephemeral world, which is also part of our physical existence of emotions, using shadows to visualize emotions, because like I mentioned, they're similar. They're always fleeting, full of potential, constantly changing. And it's a 2,215-page book where I was obsessively following my shadow every morning for a year, photographing it and then developing the images in the darkroom. And I went with this book and the pull-out table to Nantes in Grasse, where most of the fragrances are created. It's very interesting because it ranges from like Gucci sending their nose, so-called, who creates perfumes, also to psychotherapists going there and trying to heal their patients, who have post-traumatic syndrome, and they can heal these things nowadays also through fragrance because they stir up traumas and they bring back the patient directly into a situation where they first had this fragrance and bad association and can heal it. So I went to this periodic table and I said I would like to try to translate it into fragrance. And what you see here, to me personally, represents earth. It's a fragrance I created. It's mostly the national tree of Slovenia, where I'm from Linden. And I used, the image you see is actually, you can find it, its original source as a shadow in the table. And I took the three emotions, confident, loving, and interested. So this is the book. It's called Gray Matter, like in the brain, language of shadows. And I have various statements of different people about the shadow and if it has a connection to emotions. I didn't want this to be a closed project of just me. But for example, if I had known Bernard at that time, I would have asked him to give a statement. So I tried to really have different points of views. And this is another, so you can see how this image came about. And these are the actual three products. So Message from Earth, and then another product we did was Curiosity and Empathy for Earth. And yeah, this is a short video. And like I said, each one is unique and handmade, which is again goes with my kind of mission to try to, as an artist, even though I tackle more scientific and future themes, I still want to keep the physical aspect of us humans alive. So I work a lot with recycled material. And one of these is, for me, something that is keeping like human heritage alive. I call it my webs nets. So it's old pieces of fabric that usually you probably will associate with your grandma who had them like on a shelf, and you probably all want to get rid of them. Well, I was inspired to try to put them in a different context, maybe in a more manly context. And this exhibition is actually my aim at trying to create a status quo of the Big Bang, which for me, I was thinking, you know, maybe it's not a one-time event. Maybe it happens all the time also inside our cells. So I created these webs from found old pieces that I collect all over the world, and I created a sound also to go along to try to bring people into this feeling of at the same time being somewhere, you know, in deep space, alienated, but then again, feeling some kind of comfort because, you know, it all starts within us and how we perceive our surrounding. And this is another installation of mine at the United Nations last year in New York City. It was for the Earth Day. It's called One World, a World for All. And with it, as the title implies, you know, it's kind of looking at the world as our common home. It can be a cell, a mandala, an embryo, whatnot. And we humans are as much tied to it and a part of it as, you know, any other organism in that circular form. And so this is another example, a performance piece called Eden Transplanted, where I use these webs and I project my videos onto them. So for this 20-minute piece, I use a lot of imagery from CERN and also ESA, and Bernard was kind enough to provide me with sounds from outer space too. So it's a narrative story I created. What will happen if circumstances on our planet are no longer sustainable? Where will our home be? And for me, the answer is this is, I feel, as a human, kind of our only home. So I would urge people to really, you know, explore further so that we learn more about how to sustain our planet and live here. But in no way get carried away by the temptation to think there is some amazing plan B out there, because I think it's easier to try to take care of our planet. Of course, by knowing and doing experiments outside of this planet. So thank you so much. And if you want to, you know, try on the fragrance, feel free. There's also a website on the perfume. It's called www.dbe528.com. And 528 is the limited edition number of these, which is also the love frequency, so-called love frequency, that Tesla did a lot of experimentation on, and you know how our DNA can be affected by frequency, by sound, and yeah, I think that's another fascinating avenue to explore. So thank you so much, and best of luck to all of you, and I hope to maybe collaborate with some of you in some way in the future.
I would ask you, when you touch it, to follow all planetary protection measures. Yeah? So to be sure that we don't propagate some of these alien virus. But I see that you are we welcome also to spread it on our skin? This has been tested, so I see that the Space Safety Committee has approved it's used, but still when you handle it, please sterilize your hands before that. Thank you. Is that a question, maybe? This was just yes. Awesome.
I had a question. You said that for your last show, you used sound from space. I'm very curious about that. What kind of sound?
So I went through numerous websites that Bernard provided me with, like, of course, frequencies that were translated into audible terms.
Okay.
And I remember there were some, I mean, the funny thing is, like, if you listen to the end product, it's like a very narrative story, but all the materials are very much like scientific, and there's so much work to put into a kind of emotional reappreciation of them. But there were sounds like resonances, and then I also combined, because I'm interested in the space outside of us as well as within us. So of the body, for example, I used the sound of the heart, in the blood in my heart that I recorded at the General Hospital here in Vienna. and the centrifuge when you're separating different molecules from the blood, and always the human voice too, because again, it's something human and we still cannot replicate the human voice. So it's actually fascinating how many things we cannot do yet in terms of the human body.
That's very fascinating because we've been scientists, we all come from stars. So in France, there are scientists who deal with stars music. So like she lowered the frequencies, she interpreted it until bring it to audible. I believe it's something like that that you had to find. But I think that's something that goes very well with you and your personality. What you just presented, the music of the stars with your art would go beautifully.
Thank you.
Thank you for that. It was very impressive.
Thank you so much.
So another emotion to add to your database, that's what we have felt here by listening to you. Okay.
Okay, thank you very much, Eva. And our next speaker is Borghildur Indriðadóttir from Iceland originally, I think. Bernard, do you want to say a few words about her?
Yes. So it's a pleasure to have with us Borghildur, and she is a solar system artist, but that happened to be born in Iceland because she has really cosmic dimension. And she also wants to be the first artist performer on the surface of the moon. And we had the pleasure to have her visit at ESTEC, where she has already performed some of the act. We went into the Columbus module and we created a zero gravity environment for her. And we are now working on a production, actually, of this movie, the first artist performer on the moon, where we hope that one episode will be shot really on the surface of the moon. So, Borghildur, I want to give you the floor, wherever you are.
Thank you, Bernard, and everyone. It's such a pleasure to be taking part today. And we wish we could have been there in person. So thank you for having us. And here's a presentation of our upcoming project. Sabrina, do you have the link open to the Vimeo?
Yes, I can start it whenever you need it.
Okay, great. So hi from Berlin. This is Alexa.
Hello.
And Rosalie.
Hello.
The team. And you can start it right now. Enjoy.
And I'm an artist and architect. I have 10 minutes to explain to you my current art projects and most importantly, artists on the moon. My background in education comes from a variety of sources as I am a multidisciplinary artist. I finished my master's studies in architecture from the University of Arts in Berlin, but I also have many different approaches such as photography, acting, dancing. My latest work is Mask City, about how COVID affects my work, but also everyone in this pandemic. It's an interpretation of our current state of being. A performance in Berlin, which resulted in my exhibition in Tokyo being cancelled. And that you can see here on this video. The work itself is still alive. It's about Vigdís Finnbogadóttir, first female president in the world, who is still alive, beautiful and strong, 90 years old this year. And I did a work with her in Reykjavik in February this year. As you can see in these images and the video. I'm a multidisciplinary artist, but I'm also in a way, connected to many different cities. For example, Iceland is very important for me, especially geographically, and Berlin culturally. My Icelandic heritage, I'm talking about it here because it's really interesting for this whole workshop. Because it's not such a long time since my ancestors lived in a cave in Iceland, in ESPI. And we will be having a performance next year with the Moon Gallery in Stefánshellir, which is our link to future habitations, and I find it very fascinating. But how did I meet Bernard and get into this art project, Artists on the Moon? Well, we have such a mutual interest in art, and he said, for our Moon project, we need engineers, scientists, we need also entrepreneurs, and for Renaissance, we need artists. We need artists on the moon. In collaboration with the European Space Agency, Artists on the Moon, Performance for the Stars, is an unparalleled endeavor in which I travel, discover, and most importantly, perform a contemporary performance piece that will be live streamed back to Earth. Being the first woman and the first artist ever to step on the moon's surface, imagine. I continue to question gender structures and ultimately interpret and question the way in which we as humans understand our whole role within the solar system. This is a hugely peaceful gesture, and it's unlike previous mission in a way, in which national flags were raised and items of the moons were taken back to Earth, somehow as to suggest some kind of symbol of ownership. But no, Artists on the Moon does not seek to claim ownership over anything. rejected pluralistic visions of interplanetary relations and opting instead for a peaceful gesture, a performance for the stars. I hope to see some of you in person in October for my next mission simulation. Thank you so much for listening. For more information about the project, visit themoon.is.
Thank you so much for listening. And yeah, that was a bit of a loop with the video. It wasn't supposed to come on so many times, but I hope that you are inspired with this. And
We enjoyed watching it, so it was really cool.
thank you.
Are there any questions for Borghildur from the audience? Actually, I have a question. The stone that you were handling in the video, was this a stone from Iceland or?
Yes, it's a lava stone of a very young Icelandic lava from the area of Vatnajökull, which is close to Askja, where Neil Armstrong was training a couple of years ago. So I thought it was very fitting.
So you collected it yourself?
Yes. And it's the interesting fact that it floats on water. It's so light. So thank you so much. And yeah.
Thank you, Borghildur. Yeah. Yes, it was amazing to see your performance, and also a beautiful, for me, another emotion for Eva, to see that you have used some smart one images as background for some of your performance. So it was quite touching to see these images that we planned for scientific purpose, how they are integrated in your performance, and they put us already in the moon mood before we go there. So we expect also to have you inside the moon module in Poland. So we expect you in October. Some of the crew for this Poland campaign are here with us, like Roxana, and also we'll have some mission control support. So we'll have opportunity to help you in your project, and you'll be part of a crew. And also we are looking forward having a big event in Iceland. So together with EuroMoonMars, with the EuroMoonMars Chile campaign next year in May, June 2021. So we'll have Mark, and we'll have also Sabrina with us there. So I think we really like this collaboration that we have among all disciplines and working with all parts of our brain. Thank you so much.
Thank you.
Thank you, Borghildur. And now as our very last speaker for today, we have Mary Cooper, who has decided to give a presentation for us. Mary, I will hand over the screen sharing to you now, because you're going to tell us about the Moon Gallery, which is a project with ILEWG and EuroMoonMars, and about your contribution to this. So you can screen share now. Thank you.
Okay, thank you. Thank you, Sabrina, and thank you, Bernard, for inviting me to speak today about my art and the Moon Gallery. I will start share screen. Okay. Okay. This is my first slide. Because many people talked about habitats in on the moon and on Mars, and I used to be busy with habitats on Earth. And I chose this title for my presentation because I also work with nests, and I think nests are habitats on Earth. Okay, next slide. My childhood home was on a farm in the Netherlands, and the close connection between nature and farm has continued to inspire me to the present. To me, a nest is the metaphor of the source of our existence. It symbolizes shelter, fertility, and new life. It also refers to the transience in nature. It was around 2005 that I saw a blackbird building a nest in Drenthe. It's in the north of Holland, in the shape of a bowl. And I was really caught by this. And since then, I've been studying form and content of birds' nests. The thing is, when I was a small kid, I used to walk outside in nature, but never was allowed to come close to nests from my dad. He always said, no, no, you should not disturb the birds. So when I saw this bird building this nest in front of me, I felt, well, really honored. I used to cast my sculptures in the past always in bronze. And now I was thinking, how can I capture a nest? Could it be possible to cast a nest in bronze? So a period of research followed with the following questions recurred, like, from what materials is this made up? What do I have to do to prepare this nest? Can the bronze flow into the casting mold through the narrow canals? Well, these are some of the recurring questions because since then I have focused on immortalizing abandoned nests in bronze. And during this process, I burned the original nests, so each artwork is unique. Well, you can also think of empty lava tubes, I think, where you could pour in material, and branches of nests are very, very tiny many times. So it has to be possible that you can pour in the bronze and it will flow through. See next slide. This is a magpie nest that I got as a present a few months ago. I still have to work on it before it can be casted. As you can see, a lot of work has to be done. It's huge. It's about 1.5 meters. So, well, I really have to study on how to work this out. It's going to be a real challenge. When I have prepared the nest, also with the canals to pour in the bronze and the canals to let the air out, I put it in an oven, a special oven, for about 3 to 4, sometimes 5 days, depending on the size of the nest. And I've been experimenting a lot. In the beginning, also many tests went wrong because the bronze was going in the mold very hot, but the mold itself would be cold. So then in the beginning you had the bronze, but then it would not flow through all the canals. So now I'm preparing the mold with fire and to make it really hot so that the bronze will flow easier through the canals. Okay. Well, this is after the bronze has been poured in the mold. As you can see, it's still really red hot. It will take about a day before I can really start to remove the cast. Because if you do it too quick and the mold and the bronze is still too warm, it's very easy to damage the sculpture that has to come out afterwards. Well, this is the day after. These are the molds. They are waiting for me to get well to work on. Yeah, this is oh, sorry, I pushed the button. Here I'm working on one of the molds. I can start with a hammer very gently. I should not do it too roughly because I may damage the branches of the nests. I start with this hammer. It always works very well to get rid of the first layer of the mold. And after this, I have to work with smaller tools. And many times it takes, well, sometimes with the complicated nests, it sometimes takes me weeks before the mold is really out of all the holes. Here you can see that I'm a little bit further, and the branches are coming out, and it's like when I'm working on this, it's like kind of adventure. I think it's also a bit like going in a cave or whatever, because I can't really remember every branch anymore where it will be. So I really have to do this very careful. And finally I work with how do you call it, with dental tools from the dentist, and with brushes to clean it. Okay, next slide. Well, this is a turtle dove nest. I think I'm very proud of this one because I really think it really worked out very well to get to have the bronze going through all these canals. It's a very open nest because, well, that's how doves are working on their nests, just very wild branches, and they're very quick done with their nests. This is another example. This is a very special nest. This is a nest of a wren, and a wren is many times building its nest like a kind of cave, and sometimes also hard to find. The wren nest was built first, and the funny thing is that a blackbird found it and decided to build a nest really next to it and attached to it. So I always say, well, the wren and the blackbird were living apart together. That's some kind of thing I say usually. I think I made, well, maybe 50 or 60 nests now. And they're included in art collections in the Netherlands and also abroad. Okay, we move on. Here we are in June 2018. I was at Pulbry Studio a few weeks before. I was invited by Alexander Saklinski, who's also a Pulbry member, to join his workshop Art in Space. And this was the first time that I got to know about the Moon Gallery. This also is the day that I first met you, Bernard. I also remember that you gave a presentation about Lunar Village and preparing Moon Village on Earth. Well, Alexander invited me to join the open call for the Moon Gallery. And these were the questions for the open call. The overall message you want to our guide, the question one was the overall message you want to our guide for future generations, and how is the object of work of art a symbol of this message? Boy, oh boy, I was always thinking big, but now I had to think big and work small because the object has to fit in a 1 by 1 centimeter cube. Okay. Well, I have to think out of the box. I can't send a nest in a 1 by 1 centimeter cube. A nest is too big. Okay, you work with bronze. Forget the bronze because weight is something you have to take care of. Bronze will be too heavy to send to the moon. So what material do you use? What can you use? What do I want to archive? What has been important for mankind? What's still important for mankind? Well, ever since the existence of mankind, humans have explored their area. They wanted to expand. They were crossing borders, sail seas, discover new land. Now they want to visit and inhabit the moon and Mars. So I watched space-related videos and noticed that engineers and astronauts were mentioning horsepower while talking about rockets. Isn't that amazing that space-related, the word horse is mentioned? Because horse is really earth to me. It's power, it's whatever. But then, okay, horsepower. Where's horsepower coming from? I didn't know. So I started to investigate and ask questions to scientists because, well, I'm just an artist. I'm not a scientist myself. One person came up with mitochondrial DNA, the power plant in our cells, but it's also a power plant in cells of animals. And what I learned was that the follicles of hair include mitochondrial DNA and therefore also in horse hair. Well, the horse had made our expansions on Earth possible. And within 1 century of industrial revolution has made the horse redundant. Technical developments have opened the door to our galaxy and beyond. So here you see my prototype, a circle made out of horsehair, also including follicles. The inner circle, first circle I made was out of dark hair that related to Earth. And I decided to work on with lighter hair surrounded, also relating to space. And a circle also because of its strength and its infinity. That's my here. Here on the slide before, you saw my little 1 centimeter cube nest. Here is a bigger one. We were invited for exhibitions with the Moon Gallery, and the artworks were submitted in the small gallery and hard to see. So then we were asked, the artists were asked to make bigger copies, like 10 or 15 centimeters to exhibit on exhibitions. And this is the bigger one that I made, also with the black hair in the inside, although you don't see it now that it's hair because it looks a bit like the black screen on the back. And I made it a bit in this shape because it looked a bit like some kind of planet floating in space towards the moon. Well, the Earth is our nest. Humans can think and create. We're intelligent creatures who can fly independently. Birds maneuver from branch to branch, but mankind needs machine to navigate the galaxy. Well, although at the beginning of the project, I really thought I had to think out of the box, I finally realized that after my wanderings, I ended up again with the theme of my nesting. So I'm sending a nest to the moon to give a warm welcome to future astronauts and residents. And in case all the machinery stops working, they maybe can use the follicles of the hair to get some energy. Okay. Well, this is the logo of the Moon Gallery. As I told before, I'm one of the artists in the gallery. And let me introduce you to the team. The team is Anna Sitnikova, the curator and exhibition designer, Elizaveta Lugova, the curator and graphic designer, Bernard Freing, space sector expert and visionary, and Alexander Zaklinski, the gallery founder. I'm talking now on their behalf because Anna and Elisabetta were not able to join the meeting today. The proposals of and the submissions and the questions they have now for artists is, what are the ideas that we want to promote into the future, and what are the ideas that we want to leave behind? So new artworks came. Here are some pictures of the miniatures of some artists. This is from Maria Baumeister, Daria Kojena, so I hope I pronounce all these names good. This is Thomas Heitman.
Can you wrap up in 1 or 2 minutes, Mary? Because you were supposed to talk 10 minutes. Thank you.
Okay, well, these are some artworks. Here is another, here are some more artworks. Okay, I'll go very quick. Moon Gallery it's working on exhibitions, collaborations, astronomy, workshops, education, symposium, and conference. I will just go very quickly through the slides. These are some of the exhibitions that we had. A very nice exhibition of the Moon Gallery at Space Expo. And this was an exhibition at Milan Design Week, Quarter in The Hague, Vernissage in Zermatt. Here you can see the Moon Gallery attached to a lander. This is how it will be sent to space. Also, here is the lander exhibited at Prague. The gallery is on the other side. This was this year in the Glazen Huis in Amsterdam in the Amstel Park. And at this moment, we have a gallery exhibition at the old observatory. Whenever you're in Holland, it's still possible to visit this exhibition because it will be there till December. This is a new way of exhibiting with not in the small cubes, but just in a bigger cube. So there's more space surrounded the small miniatures to show. Here is the Moon Gallery, of which I think will be the first Moon Museum. As you can see, there's some spaces left for IDs. So if you feel like sending an ID to the Moon Gallery, that's possible. You can submit it to art@moongallery.eu. It's the address of Anna and Elisabetta, and here is the website of the Moon Gallery. And thank you. Sorry if I took too much time.
Are there questions from the audience? Not so far.
I just brought one mock-up of the Moon Gallery that we bring us to Vienna. You can say, oh, we had one road to Vienna.
Yes.
Yes, as you see, it's a way that we want also to connect to the society at large, and having artists a bit also as ambassadors to bridge to the society. And so I think it's a way also to consider that when we have an habitat on the moon, we have also to have a room for other type of activities and science, technology, or resource exploitation, but also we need to have inspiration activities, educational activities, and artistic activities. So on this, I think that's a way to conclude our workshop, but I want to give the word to you, Sabrina. I want to really to thank you for really organizing all the program and also the logistics. I thank you also you to be participating in this very exclusive club of those that could come in this ESPI spaceship. And I want also to thank all our audience worldwide on YouTube for today and also in the future, because this show will be recorded and eventually we will make history when people will look at it from the moon base in the future. So I leave the floor to you, Sabrina. In the meantime, I'm going to call also Jean-Jacques.
Thank you, Bernard. Thank you for co-hosting today. And of course, a big, big thank you to our generous host, ESPI. I think they deserve a round of applause from us. Maybe they heard it back in their offices. Well, I really wanted to thank you all for taking the time today to come on a Saturday. It's a beautiful weather outside, hopefully not the last sunny day, but we really appreciate that you took the time today. And for all of the really great presentations that took us to the moon, took us to robotics, but always somehow connected to space habitation. And I think we all learned a lot and engaged a lot. So you're all very well.
All the, I would say, manned space, science and exploration related I would say topics higher on the agenda of ESPI. And definitely, I think that we will keep in touch with Professor Foin and well, to all of you. Thank you again for your kindness. You have been very, very nice guests. Thank you.
So, okay, so that is closing our event. So on the practical side, so we will, do we need to do anything for the living the place as we found it, things that are okay? Yeah, okay. Yeah, okay. So the plan is take the dishes. Yeah, all the dishes.